Good morning, everyone. My name is Anna Teti. I'm Professor of Histology at the University of L'Aquila and Chair of the TMS Executive Committee. I would like to welcome you to the TMS Day, in which we will complete our annual activities with lectures and representations by guests and TMS members. So the TMS stands for Thursday Morning Science because we meet every Thursday and is organized by a group of talented and passionate students and young investigators. Our activities are interdisciplinary, ranging from physics to chemistry to biology, biotechnology, and biomedicine. So we have weekly webinars, seminars, career development sessions, journal clubs, and other activities. And everybody can contribute to the program, and you may receive regular information visiting the TMS website and registering for receiving the notifications of our activities. So today we have a very rich program with 3 experts lectures and 9 oral presentations. At the end, the best presentation for each category selected by independent reviewers will receive an award in recognition of their effort. So I don't want to take more time, so I would like to ask Marco to provide some housekeeping information. Thank you and have a great day.
Okay, thank you and good morning, everyone. So I'm just going to be brief and tell you a couple of housekeeping rules for the day. And this is for all the attendees. All the attendees should be muted, so please keep your microphones off. And the cameras should also be off. So please, those of you who are not going to speak should turn the cameras off. And this is to keep the connection let's say, lighter and easier for the viewers to understand who is speaking and who isn't. And so the recording of this series of seminar will be available on our YouTube channel soon. But you can also follow all of the sessions live on e-learning Univac, the link I'm sending now in the chat. So you can go there thanks to Maurizio Cironi, who set up the link for this. So thanks again, Maurizio. And we have this personalized link within the University of L'Aquila. So apart from that, if you have a question, please ask it through the chat. So you can just go into the chat and ask your question, and the chair of the session at the end of the seminar will just read it out loud. This is the only way to keep the questions inside the seminar recording. So please use the chat. Do not activate your microphone unless you are prompted to by the chair. Okay? So thank you very much, and I hope you enjoy this day. And I will now give the word to Francesco Saramida to start the scientific part of the day. Thank you.
Hello, everybody. So thanks for coming to the TMS Day of Science, and so it's a pleasure for me to start this day introducing Aldo Ianni, which is our first speaker. So just a few words about Aldo. He's a researcher at the Gran Sasso laboratory, and among the other things, he's a former student of a former PhD student of the University of L'Aquila. He joined many collaboration, many experiments, always in Gran Sasso, mainly in Gran Sasso, during his career, Dark Side, Warp, Borexino. He was a reviewer for many other experiments, and among the other things, important things, he was the director of the underground laboratory of Canfranc between 2015 and 2018, and at the moment is the director of the NOAA infrastructure that is at Gran Sasso laboratory. So I will not take too much time to the speaker, so I give the word to him. So please, Aldo, go ahead with your presentation. Thanks a lot for being here today. Aldo, we cannot hear you.
Okay. So good morning to everyone. Thank you for the introduction, and thank you for inviting me to this event. I will share the screen. And get started with my presentation. So I'm going to talk about dark matter direct detection and giving you some examples on the activity carried out at the Gran Sasso laboratory. So here I have some useful numbers which I'm going to use in the following discussion, and you can take them into account for further readings of this presentation. So to get started, let's take a brief tour in the nearby universe. So we are going to talk about the region around the Sun in the Milky Way on a scale of about 700 parsec. We're going to talk about the Milky Way in its large size, horizontal size of the order of 30 kiloparsec, about the Andromeda Galaxy, which is the closest galaxy to the Milky Way at about 800 kiloparsec in the local group, another galaxy 9138, 16 megaparsec, and about the Coma cluster, which is much further away at 100 megaparsec. So this is an example of the local group. The extension of this group is of the order of 3 megaparsec. So here is you can see our galaxy with some satellite objects, such as the large and small Magellanic Cloud and the Andromeda M131 galaxy, which is the closest and largest galaxy to the Milky Way. Both the Milky Way and the Andromeda galaxy are in relative motion. In particular, standing from our galaxy, the Andromeda is falling toward us at a speed of about 100 kilometers per second. And this is important for the consideration we're going to make later. So this is an example of the Virgo supercluster. So we are going away from the local group where we meet this galaxy 9138. And this is a much larger view of the universe, where you can appreciate the structure of the universe, which, as we understand today, is due to the dark matter we are discussing here, with many voids and filaments of a cluster of galaxies. So the extension is more than 100 megaparsec, and the profound understanding that we have about this structure today is that without the present amount of dark matter, this would have been very much different. So if we now focus on the Coma cluster, so on the left side, here you see the visible spectrum of this cluster of galaxies. And this gives you some idea of what is the amount of mass in the galaxy, in the cluster, from visible light, visible objects. On the other hand, however, if you span this cluster of galaxies in the X-ray spectrum, then you have a completely different image, which you can see on the right side. And you can appreciate that the amount of mass embedded in this cluster of galaxies due to gravitation force, it's much larger than what you can appreciate just looking at the visible objects. So as a matter of fact, the mass of the gas is much larger than the mass of the galaxies. So this is one example of the way we should look at the universe, spanning in different spectra our observation in order to determine the real amount of matter in the universe. The first exercise was done about 90 years ago, in 1933, by a Swiss scientist, Zwicky, who studied the relative motion of galaxies in the Coma cluster. And what he realized was very profound and started the idea of the dark matter in the universe. So as we know today, the Coma cluster is made of 1,000 galaxies over a 1 megaparsec size. However, in 1933, the radial velocity was known only for a very small number of galaxies, which had a dispersion velocity of the order of 1,000 kilometers per second. So from this observation, Zwicky can determine the mass of the cluster to be of the order of 10 to the 15 solar masses. And what he did was simply to make use of the virial theorem to account for the global mass of the cluster. And what he realized is that the total mass, which keeps the galaxies in a gravitational in a cluster due to gravity, it's only it's much larger than the luminous mass. As a matter of fact, the mass to luminosity ratio for this system of galaxies is of the order of 200-300, measured in unit of solar mass to luminosity of the sun. So this was the first fundamental evidence that in the universe there is a huge amount of non-visible matter which can interact due to gravitational force, but not to the electromagnetic force. Then later, other scientists studied the so-called rotation curves of galaxies. And as a matter of fact, this is the most convincing and direct evidence for dark matter on a gravitational scale. And the conclusion that now we can draw today is based on several measurements of the circular velocity of stars and gas as a function of the radial distance from the galactic center. And this has been carried out over many objects. So in order to look at this into more detail, we know that when we have an orbiting mass, small m, about a large mass, large M, capital M, the velocity as a function of the distance decreases as the inverse of the square root of the radial distance. So this is a well-known law based on Newton gravity. And this is very well in accordance with the movement of planets in our solar system. We know that in our solar system, the mass of the sun is about 1,000, a little bit less than 1,000 times the total mass of planets. So it's essentially the planets are orbiting around a point-like mass. And they really follow, as you can appreciate from this curve, the 1 over square root of r law. So we expect the same behavior for stars orbiting around the center of the galaxy. So in 1970, Vera Rubin studied the motion of stars around galaxies, the center of galaxies, where for each galaxy we have about 10 to the 11 stars. So the result is the following. Here you can see on the y-axis the velocity in kilometers per second, and on the r-axis the distance to the center in units of 1,000 light years. The scale goes from 0 to about 17 kiloparsec. So you can see that the data do not follow the expectation from visible matter, which drops, as we expect, as 1 over the square root of r. On the contrary, the velocity increases, even at large distances, and this is completely in disagreement with the expectation. So these stars around 10 kiloparsec, they move so fast that in principle they should leave the galaxies and no longer be trapped by the gravitational force. So let's have another look at this important result and take into account the galaxy 3198, which, as we said, is about 16 megaparsec away from our galaxy. So this is the plot of results, where you can see that above 10 kiloparsec, the velocity is almost constant, of the order of 150 kilometers per second. So all the stars with a distance larger than 10 kiloparsec, they move really very fast, and they do not follow the expected trend determined from Newtonian gravity. So they move so fast that, as a matter of fact, they should not be trapped by the gravitational force. So what is causing this behavior? So one important and the most convincing scenario today is that there is dark matter embedded in the galaxy, forming a so-called dark halo surrounding the galaxies. And if you take into example a simple system to fit the data, then you can see where that a dark matter halo can really reproduce the trend at large radii. As a matter of fact, what happens is that the total mass of the halo within 30 kiloparsec, it's 2 times the mass of the visible matter. So in the end, the mass to light ratio for this galaxy is of the order of 11 in the same units. So again, we have 10 times more matter than the visible matter. So this matter is what after Zwicky is called dark matter. So how the dark matter is distributed in the universe? So if we look at different scales around the sun and so on, up to the cosmological scale, we have a peculiar trend. So around the sun, this is the results. Here we see the mass to light ratio for due to stars, dead stars, gas. And this 50 over 15, it's about 3, which is less than what determined from relative motion of objects in this volume about the sun. So the mass to light ratio is smaller than what we have seen on a galactic scale, but is still larger than the standard matter to light ratio, taking into account only known objects. If we move to the galactic scale, and at some point we make the consideration that the dark matter halo should have a finite size, the maximum velocity measured is of the order of 500 kilometers per second. So the extension related to this maximum velocity is of the order of 40 kiloparsec. And if we take this number into account, the mass to light ratio that we determine from this observation is of the order of 30. So again, it's larger than within the 30 kiloparsec scale, and in a region of galaxy. Now, if we take a larger view and we consider the dynamic between Andromeda and the Milky Way, the relative motion, as I said, the Andromeda is falling toward the Milky Way at a velocity of about 120 kilometers per second. The relative motion allows us to determine the mass embedded in this system. And again, we see that the mass to light ratio is of the order of 100. So increasing the size increases the amount of dark matter. So this is the trend that we can take into account from these observations. And we see that when we arrive at about 1 megaparsec, the mass to light ratio is determined in order of this omega, which is the relative density relative to the critical density of the universe, is of the order of 0.3. And for size larger than 1 megaparsec, this behavior flattens. So we arrive at a point where we determine the total mass of the universe, which is dominated by dark matter. So another important example I'd like to make is the one about the bullet cluster. So this is an example of two colliding cluster of galaxies and gas. This observation was done in 2004, considering the collision between two galaxies in interaction, moving at a relative velocity of about 4,500 kilometers per second. And this is the most important evidence of dark matter at megaparsec scale. So this is the famous picture of the bullet cluster, where in blue you see the distribution of dark matter from gravitational lensing, and in red you see during the collision the distribution of gas, and you really can appreciate the difference. Though the gas is interacting and is producing this peculiar distribution due to the collision effect. On the contrary, the dark matter is not interacting and stays almost undisturbed during this collision. So what we learn from this lesson is that the dark matter is almost collisionless at 1 megaparsec scale, and we can determine from this a sort of cross-section interaction for dark matter particles. From the study of galaxies, we can determine a lower and upper limit for dark matter particle mass, which has a very wide range. So really we have something unknown in our hands, and this unknown can have, if in terms of particle, can span in a huge amount, in a very, very large range of possibilities. So in order to really try to understand what dark matter is made of, there are different possibilities. So the most motivated one is that the dark matter is made of so-called WIMPs, weak interacting massive particles, and this, as a matter of fact, has been the main object of direct experimental detection of dark matter over the last 20 years. So this is a particle expected to have a mass which goes from 1 to 100 GeV and even a bit larger. The other possibility are axion-like particles. As a matter of fact, there is some motivation from a theoretical point of view for the existence of these particles, so-called QCD axions, and they could account for the dark matter if they have a mass of the order of 10 to 100 micro eV. So it's a completely different scenario. On the other hand, the most obvious candidate is the so-called sterile neutrinos. This because we know that neutrinos, they exist. We know other evidences for neutrinos, and we can simply add a neutrino which is a sterile neutrino, so not giving rise to weak interacting processes, which might decay to an active neutrino producing a photon, and this will give a hint of the existence of these sterile neutrinos. So, what is the experimental method to detect dark matter particles? There are three possibilities. So one possibility is the indirect method, where you imagine that two dark matter particles, a particle and an antiparticle, they annihilate, producing standard model particles. So this is effective in regions in the universe where the density of matter and dark matter is pretty large, so the probability of interaction is large in spite of the small cross sections. And so mainly are like the center of the galaxy. In our close nearby region is the center of the sun, for example. So these are possibilities, and you have an indirect measurement because you detect the product of this annihilation. Another possibility is to produce dark matter particles, and this can be the case in colliders, where two standard model particles, they annihilate, producing dark matter particles. Although here one should notice that at some point one in a different method, with a different method, should prove that the particle produced are really relic particles, so they can live for a very, very long time, comparable to the lifetime of the universe, in order to account for real dark matter particles. The other possibility, which is the one I'm going to discuss in more detail here, is the direct detection of dark matter particles, where a dark matter particle interacts somehow with a target particle from standard model particle, producing a recoil particle which gives some macroscopic signal we can measure. So let's focus on the direct detection. So in this case, we have an interaction between a hypothetical dark matter particle and the nucleus. So the dark matter particles in the surrounding of the Earth is moving at the velocity of about 300 kilometers per second, and this will give rise to a recoil energy, nuclear recoil energy, of the order of 1 to 100 keV. So it's a very low energy. As a matter of fact, this particle at this velocity and with this mass can be associated with the Compton wavelength of the order of the size of the nucleus. So the expected energy spectrum for this kind of interaction depends on a number of parameters, and here you can see in particular that they depend on rho chi, is the density or local density of dark matter, depends on the mass of the dark matter particle, depends on the interaction cross-section, and depends on the velocity distribution in the galaxy of these particles. So these are there are a number of unknowns in this spectrum rate, which must be determined from experimental data. So if you use this idea and we apply this idea to a number of targets, this is what you obtain as a result. This example is given for a dark matter particle of the order of 100 GeV and an interaction cross-section with a nucleon of the order of 10 to the minus 47 square centimeter. It's what we expect. So it's a very small cross-section. And here you see the number of events given in unit of keV per year per ton as a function of the recoil energy in unit of keV. So you see that for xenon, germanium, argon, the spectrum is featureless. And this makes the experimental study very, very challenging. In addition, the number of events expected for this very small cross-section is very tiny. It's 2 events per ton per year. So this again makes the experimental measurement very challenging. So asking for very low background detectors and large size detectors. So let's discuss a little bit the signal versus background. So the signal, as we have said, it's a low energy nuclear recoil. The rate is very small for the expected cross-section, and there is no specific feature in the recoil spectrum. The background that we should take into account is the electron recoils due to natural radioactivity, electron, beta decay, gamma decay, and also to nuclear recoils due again from natural radioactivity, such as radiogenic neutrons or neutrons induced by muons. And in addition, due to the very low rate expected, also solar and atmospheric neutrinos, producing both nuclear and electron recoils, are an important source of background. So, and taking into account that neutrinos, they have a very tiny interaction rate, these enhance the difficulty to detect dark matter particles. So the effort done in this research, it's spread on different continents in underground labs, including the Gran Sasso laboratory here in L'Aquila. So, and there are several experiments carried out in different underground laboratories for searching a hint of interaction due to dark matter particles. So let's take a few examples about what is being done at Gran Sasso. This is an image of one detector which is running at Gran Sasso. It's the Xenon Detector. It's a time projection chamber with liquid xenon. You can see here the time projection chamber inside it's a cage made by copper rings to shape the electrical field. And this chamber with photomultipliers that you can see here at the bottom is installed inside the cryostat to keep the xenon liquid. So this is another example. It's the Darkside 50 detector running at Gran Sasso with not liquid xenon but liquid argon. Inside a water tank, similarly to the xenon case. The water tank works as a muon veto to decrease the background induced by cosmic muons. And of course you want to be underground to have very few muons and producing a small background for your dark matter search. How this method works? So here you see the example with argon or xenon. So you have a target volume made of liquid argon or liquid xenon inside a time projection chamber where you have an electric field and you have two planes of photomultipliers, one at the bottom in contact with the liquid and one at the top in contact with the gas. Because at some point close to the top you have a small interface with between liquid and gas with a different electric field. What happened is that an incoming dark matter particle will interact with the nucleus inside the target, producing a scintillation light. This scintillation light makes the prompt signal, and the prompt signal is detected is detected by the photomultipliers in the lower part and in the upper part, and at the same time, this gives the time zero for the event reconstruction and the amount of energy released by the interaction. In addition, together with photons, close to the interaction point, a number of electrons are formed. And these electrons, a fraction of them will not recombine in the liquid, but due to the electric field, they will move upward until they reach the interface with the gas. At that point, a second electric field will extract a fraction of these electrons, producing a second scintillation signal, which gives a heat in a number of photomultipliers in the upper part, mainly. So the drift time between the prompt and the second event, which is the delayed event, determines the z coordinate of the event. On the other hand, the distribution of the heats in the upper photomultipliers layer determines the x and y position. So in this way, one can fiducialize the event and reject events coming from the region close to the boundary of the target liquid, which could be mainly due to background. So this is an important effect in order to reduce the background. The other important effect due to this prompt and delayed signal is that the feature of the prompt and the delayed signal are different, and they are different for nuclear recoils, which are the candidates for the dark matter interaction, and the electron recoils, which are due to background. And this is an example where you can determine some figure of merit, like it's done in this plot, and distinguish. We can go later in detail if you have a question about this figure of merits, and determine a distribution for electron recoils, which are mainly background, which are background, and nuclear recoils, which are possible candidates for dark matter. So here you can really reject the most of the electron recoils, and so the most of the background. So this time projection chamber is a very powerful object in order to search for dark matter interaction. So before I conclude, let me say that there are two important signatures, experimental signature for dark matter interaction. These are very difficult to detect from an experimental point of view, but it's within the target of the present experimental effort. One is the daily forward-backward asymmetry of the interactions due to the rotation of the Earth. As you can see in this image, if you have a detector located in one point, the incoming flux of dark matter particles coming from a specific direction. Of course, during the day, the rotation of the Earth will change the relative position of the detector with respect to the incoming direction of particles. So this gives an asymmetry of the daily expected interaction rate. On the other hand, there is also an annual modulation due to the motion of the Earth around the Sun, the Sun, and the Sun around the galactic center. In this image, you can see that the Sun is moving at about 200 kilometers per second around the galactic center, and at the same time, the Earth is moving around the Sun at 30 kilometers per second. So this motion, and you imagine that the dark matter halo is static with respect to the galactic center. So in this way, you can see that over 1 year, you can have a maximum or a minimum of the interaction rate depending on the relative motion between the Earth and the dark matter halo. And as a matter of fact, if you put the numbers in the expected interaction rate, you see that there is an annual modulation with a maximum expected in early June and a minimum expected in December. This annual modulation has been observed by a dark matter detector at Gran Sasso, namely the Dama Libra experiments. It's the only and the first evidence of a possible annual modulation of dark matter, which need to be checked by the other experiments. And as a matter of fact, there are already other experiments taking data in different laboratories and an effort carried out at Gran Sasso to check these important results. So this, and then I go to my conclusion, is the present status of direct dark matter search in the scenario of spin-independent dark matter-nucleon interaction, where you can see the, as a function of the dark matter particle mass, which is one of the unknown, the cross-section, the interaction cross-section. And in this shaded region is the so-called neutrino floor. So it's the nuclear recoils induced by solar neutrinos and atmospheric neutrinos in the low energy below 10 GeV by solar neutrinos and above by atmospheric neutrinos. So going beyond this neutrino region, it's very, very difficult from an experimental point of view, and as of today, still there is no clear method to how to face this point. So the present experimental effort is to reach the neutrino floor and try to discover or reject the space of parameters in this kind of interaction. So you see that the Gran Sasso Xenon one-ton experiment, which is in an upgrade phase at the present time, provided the best lower limit for this kind of interaction. And we are very proud about these experimental results. So the idea is the target to reach within 2055 is to go down to 10 to the minus 47, 48 square centimeters for the interaction cross-section. So in conclusion, so we have been dealing with the idea of dark matter since 1933. The understanding of what the dark matter is made of is one of the most important open problems in basic science at present. And this because from cosmological model, the dark matter makes about 27% of the energy budget in the universe and 85% of the matter existing in the universe. So it's a dominant component, and we should really know what the dark matter is made of. So the present direct search includes several large experiments in different underground laboratories. It's a long effort done over the last 20 years. Lots of improvement has been done in the technology to face this important challenge. So I thank you for your attention.
Okay, so thanks a lot for the very comprehensive and complete talk. So I think there are few. So there is okay. First question is for Aldo is the existence of sterile neutrinos for dark matter models could be observed also in the flavor oscillation of extragalactic neutrinos.
Well, the mixing of neutrinos, of course, plays a very important role in this scenario with the sterile neutrinos as hypothetical particles. And so as a matter of fact, there is also a small hint of a few keV neutrino from the galactic center, but it's still to be clearly understood. So from extragalactic neutrinos, I'm not sure, because you should see the decay of these neutrinos. So essentially, what you observe is the annihilation of the neutrino. So you observe an indirect product of this annihilation. So it's a different matter with respect to extragalactic neutrinos or galactic neutrinos coming to the Earth. I'm not sure that you can do that that kind of observation.
Okay, another question from Marco Ponsetti is a naive question, so this is the starting. Has a weight shift from standard matter to dark matter or vice versa been observed? Is one of them coming from the other? So I think the idea would be if dark matter and standard matter are the same, if you have an oscillation between standard and dark matter, and if you can find, if this is the case, you can find some way to measure this change of mass. This is what I understand.
This I don't know. We can imagine that dark matter is not made just by one particle. As ordinary matter, we can have several dark matter particles, and so maybe WIMPs, they exist together with axions, or maybe sterile neutrinos, so they exist, but the transition between dark matter and ordinary matter, I don't know. There are theories where you can maybe have an exchange between an hidden sector to the observed sector, but this, I don't know about that possibility.
Okay, so then I have a question that maybe, so do you think, so I don't know, as far you know, there are alternative theories apart of dark matter, I don't know, modification of gravity or things like this that can in an alternative way explain the mass deficit that you have in the universe?
Well, this is a very important question, and as a matter of fact, at galactic scale, there is a theory known as the Mondra Theory, which modifies a little bit the gravity at galactic scale. It could account for the rotational curve observation. This is true. However, this possibility, as far as I can tell, cannot be extended to larger scales, and in particular to cosmological scale. So at cosmological scale, a modification of the gravity which could account for what we observed in terms of structures in the universe has not been proposed and found at the present time. So the answer is that, at least the standard answer is that no, this is not possible.
Okay, so I don't see other questions, and I think the talk was very clear. Okay, there is one from Professor Teti. Okay, I have a question outside the talk related to the current conjunction between Jupiter and Saturn. Is there anything naive people should know to enjoy it? Is there anything naive people should know to enjoy? I think it's about observation of.
This I don't know about that. I'm sorry. It's an interesting question, but I don't know.
Usually we study the sky, but we don't look at the sky more often, I have to say.
Of course, this from underground, it's a different view of the universe, and also in detecting neutrinos from the sun from underground, it's a different way to look at the sun itself, and so on. So it's a different observation method to the universe, similarly to the gravitational wave detection, for example. It's a different window to look at the universe.
Okay.
No, of course, I also see from my house Jupiter. It's okay.
Yes. Now there is also the comet in the sky. That I didn't see it. But now,
yes, we should make a T-shirt. It's a good idea.
Okay, so thanks again to Aldo for the talk, and it was really a pleasure to have you.
Thank you very much for your attention and for your invitation. So now I close the sharing connection.
Okay, thanks a lot.
Enjoy.
Okay, so let's go to the next speaker, that is Valerio D'Andrea. Valerio is here, I don't see him. Valerio?
Yes, I'm connected.
Okay, Valerio, let me introduce a bit Valerio. Valerio is a postdoc in the University of L'Aquila. He's currently working on Xenon and partially on Gerda, where he worked for many years among the other things, Valerio is, I think, one of the first student of the PhD school of GSSI, and now basically is working also on dark matter, but he had many years of experience on GERDA, and I think he will speak about it today. So Valerio, please go ahead. Thanks a lot.
Okay, thanks Francesco. So I will start to share my screen. Okay, can you see my screen?
Yes, we can see.
Okay, so okay. In this talk, I will talk about one of the main research topic also of the Gran Sasso laboratory, that is the Neutrinoless double beta decay search, and in particular I will focus about this experiment that is called GERDA, where I worked for many years, and also about this legend experiment that is a new experiment. So I will start to say something about the neutrino, that is what we are studying. The neutrino is a very interesting particle that has been discovered in 1956, but was known since 1930. The neutrino is a fundamental lepton particle, like for example the electron, but is neutral. So this means that can interact with matter only through that is called weak interaction. So this means that it is quite difficult to understand the properties of the neutrino. What we know and what we observed is that the neutrino has three flavors: the electron neutrino, the muon neutrino, and the tau neutrino, and we are observing an oscillation in these three flavors. So, but from this oscillation we know that the neutrino has a mass that is very little, also compared, for example, the electron mass. But the situation is not so simple, because the so-called mass state that we can see here in this plot in the right are not corresponding to the flavor state, but they are a combination of these two states, as we can see from this color here, that are corresponding to the three flavor state. From this relation we know that there is a difference between these three masses. For example, this is coming from the atmospheric neutrinos, and this little difference here is coming from the solar neutrinos. But for example, we don't know the ordering, so if this is called the normal ordering or if this that is called the inverted ordering. And also we don't know what is the absolute scale of the neutrino mass. And another thing, we don't know if the neutrino is a Majorana or a Dirac particle. That means that we don't know if the neutrino and the antineutrino are the same particle or not. So to understand more about the neutrino, what we do is to search for this decay that is called the neutrinoless double beta decay. Here in this Feynman graph, I'm reporting the double beta with the emission of two neutrinos. That is a decay that has been observed in several isotopes with a longer half-life of the order of 10 to 19, 10 to 21 years. But this has been observed, while this other decay, that is the neutrinoless double beta decay, where we don't have neutrinos in the final state, is an hypothetical decay that up to now has been never observed and is predicted with a very long half-life of the order of 10 to 30 years. The observation of this decay implied that the neutrino has a Majorana nature, implied that we have a violation of the lepton number, that is something that is not allowed in the standard model of physics, and also through the measurement of the half-life we can say more about the neutrino masses. So what we expect, what is the signature of this decay? So here in green you can see the continuum energy spectrum. Here in the horizontal axis we have the energy. So in green you have the spectrum of the double beta with emission of two neutrinos, that is a continuum spectrum with an endpoint, while the hypothetical signal for the neutrinoless double beta decay is a peak at a precise energy, and this is what we are searching for. For example, here you have reporting the peak expected for the germanium-76 isotope that is used by Gerda, that is around 2 MeV of energy. So now I will start say something about Gerda. Here you can see a nice picture of the experiment, and in particular, in the center, you can see the core of the experiment, that are these germanium detector. The germanium detector, you can see here one example, are not normal detector because they are enriched in the germanium-76 that, as I said, they can decay through double beta. And this means that our detector is also the source of our experiment. And so the goal of this kind of experiment is to shield against the every external radiation. So what we do in Gerda is to build an array with 40 germanium detector that then we put in this volume that is called liquid argon veto, that is used to shield against the external radiation. And this is inside, as you can see from this picture, a liquid argon cryostat that is used as both cooler and shielding. This liquid argon cryostat is inside a so-called water tank that is also a further shield against external radiation. As I said, this infrastructure is underground in the Gran Sasso laboratory. Here I'm showing you the results, the final results of the Gerda that has been presented 2 weeks ago, so are very recent results at the Neutrino conference 2 weeks ago. Here you can see in red the events that we see in our data taking. Using this data, we in Gerda are able to give the lowest background level ever observed in this field, that is of 5 times to 10 to minus 4 counts, that is this green line here. And also, as you can see here, that where we expect the signal, we have no observation of the neutrinoless double beta decay, but we are able only to set a limit that is of 1.8 times to 26 here, that is also here the best limit ever achieved by a double beta experiment. So, but what is the status of the search of this particular decay? You can see the status is this plot here, where in the horizontal axis there is the highest neutrino Majorana mass, while here in the vertical axis there is what we measured in our experiment, that is the Majorana neutrino mass. I'm reporting the results of 3 experiments that are Gerda, that is using the germanium-76, another experiment called Kamlan-Zen, that is using the Xenon 136, and the core experiment using tellurium, that is also an experiment placed at Gran Sasso. Here you can see the limit and the corresponding limit on the Majorana mass. That are reported also here. So, and while in green and in red, you can see the theoretical prediction for the Majorana mass. The goal of our experiment is to go down in this plot here, and the goal is to now to cover this region and start to look for this red region here, that is the normal ordering region, that is the one favored by the oscillation experiment. So just as I said, Gerda has finished his data taking, but in parallel with Gerda there is another experiment called Majorana in the United States that is using the same technique and now is still running. These 2 experiments merged in a bigger experiment that is called Legend, that also is using the same technique with the germanium-76. And the goal of Legend is to reach an half-life of the order to 10 to 28 years in the next years. Here you can see the goal of legend. That, so, as I said, is to cover the inverted ordering region and start to look for the normal ordering region. So as I said, the goal of legend is to reach 10 to 28 years. Legend is a bigger experiment with more than 250 members and is based on the techniques used also from Gerda and Majorana. Okay, I'm at the summary of my talk. As I said, Gerda reached the important milestones in the search of the neutrinoless double beta decay, reaching an excellent energy resolution, reaching the lowest background level of 5 times 10 to minus 4 counts, and the highest limit on the neutrinoless double beta decay with 1.8 times to 26 ER. This is the highest limit ever observed. And as I said, Gerda now finished his life, and the search of this decay with the same technique will be continued by a bigger experiment and a bigger collaboration that is legend, with the goal of reach an half-life of two order of magnitude higher than the one of Gerda. This is a very difficult task, but the first phase of this legend experiment, that is called the Legend 200, is now in preparation at Gran Sasso, and we aim to start the data taking next year. Okay, thanks for the attention.
Valerio, thanks a lot for the talk. So, if there are questions, please, to Valerio, also fast question. Okay, there are no questions, but I would like to ask you something that is. What was the most difficult things that you had to face during your career into such an experiment that seems very, very difficult to be performed?
Yeah, for sure. The most difficult thing is to, as I said, is to go down with the background, because as I said, Gerda is using the detector also as a source of the decay, and the main goal of this kind of experiment, and also for the next phases, is to go down with the background level. So to shield and to find new ways to shield against external radiation, or also radiation coming from the material that you use to build your experiment. So I think that this is the most difficult part of this kind of experiment. That is the same also for example, Darmacter experiments.
Okay, so I don't see any other questions, so let's thank Valerio again for the talk, and I will call the next speaker, that is Riccardo Biondi.
Okay, I stop the sharing.
Yes, Riccardo, are you there?
Yes.
Okay, so just I will introduce Riccardo. Riccardo is a former researcher of the University of L'Aquila, where she was a theoretician, basically. Now he converted to an experimental physicist and is working in Gran Sasso, and is working both Boron-Xeno experiment and Xenon experiment. And today he will speak about neutrinos from the sun. And I think we will speak about Boron-Xeno, basically, yes. The recent result that we have from Boron-Xeno. So please, Riccardo, go ahead with your talk. And again, if there are questions, please write in the chat. Don't be shy.
Can you see my screen?
Yes.
Okay, now you should see the slide.
Okay.
Okay, sorry. Can you also see my pointer?
Yes.
So I can use to point something. So I'm here to talk about these very fresh results from Borexian experiment, which is the first direct experimental evidence of Sieno neutrinos. So as we already know, the Sun is powered by nuclear fusion. The net results of this process is that you have 4 protons that are transformed into a helium nuclei, 2 positron, 2 neutrinos, and they release around 26 MeV of energy. This process is carried on by 2 mechanisms. The main PP chain reaction, which is we produce 99% of the energy, and the subdominant Sieno cycle. On this plot here, you can see the energy spectra of the various neutrinos that are produced in these reaction chains, and also you see the different techniques of detection that are used and to which kind of neutrino they are sensitive. And summing up everything, we have a neutrino flux on Earth that is around 10 to the 11 neutrinos per second per centimeter square. And a precise measurement of the different components of solar neutrinos flux can be used to address many interesting topics in astroparticle physics. So, as it was said before, we use the Borexian detector for try to detect these solar neutrinos. It is located at the underground laboratories of Gran Sasso, and it is optimized to detect elastic scattering between electron and neutrinos. That happen into this inner vessel, which is a sphere of 4-meter radius, and it contains 300 tons of liquid scintillator. The interaction between electron and neutrino happen in this scintillator that produce light that is detected by around 2000 photomultipliers that are located around this sphere. Borexian has unprecedented scintillator radio purity, a very low energy threshold, and a high light yield. It has also good energy and position resolution, and it can do also particle discrimination, but it is not sensitive to directionality of the incoming particle. Here is a brief timeline of the Borexian history. So we started in 2007, and also in the phase 1 we were able to measure the beryllium-7, boron-8, and PP neutrinos. Then, after a purification campaign that reduced the background to an incredible level, the contamination of thorium and uranium is 10 to the minus 19 grams per grams, which is never reached before. And we started a new phase where we measured also PP flux and enhanced the measurement of the other components. Then in the recent year, we started thermal insulation of the detector to prepare the phase 3, in which we were planning to measure the Sieno neutrinos. Sad part is that Borexian will be decommissioned by the end of the year, but we are going to end with a bang, so we are going to have final results. Why Sieno neutrino detection is so important is because this could be the first proof of energy production in stars via the Sieno cycle, which is known to be the dominant energy production mechanism in stars heavier than the Sun, and it could also give an hint about the amount of heavy elements into the Sun. What is the challenge of this detection? Of course, we have very few events of expected events of Sieno neutrinos. We use this unit of measure, which is count per days per 100 ton of scintillation. We expect around less than 10 count per from Sieno neutrinos. And also, as you can see from this picture, the spectral shape of the Sieno neutrinos is very similar to the one from PEP neutrinos and from bismuth-210 beta decay. So this implies a strong correlation between these three species that needs independent constraint on the two backgrounds to disentangle them from the Sieno signal. Regarding PEP neutrinos flux, it can be constrained at 1.4% level through the solar luminosity constraint coupled with robust assumption on the PP to PEP neutrino rate ratio, also on existing solar neutrino data and the most recent oscillation parameters. So it is a very robust constraint. Other story is for the bismuth rate. We have to use different techniques. The bismuth rate can be constrained from its daughter nucleus, which is polonium-210. As you can see from this decay scheme, at secular equilibrium, the rate of bismuth-210 is equal to the one of its daughter nucleus, polonium-210. And why this is important? Because polonium events can be easily detected because they produce monoenergetic alpha peak, a very clear Gaussian peak on the spectra, and they can also be discriminated from beta events using analysis on pulse shape. But there is another problem, because the polonium intrinsic rate, the one that comes from the scintillator itself, is perturbed by the presence of strong convecting motion that contaminates the fiducial volume with additional polonium coming from the inner vessel. So the collaboration made a huge effort to stabilize experimental hole temperature and insulate the detector. So then the quest for CNO is turned into a quest of bismuth through polonium. We monitor the behavior of the polonium event into the detector, and we need to find a region in the fiducial volume where the rate of the polonium is at its minimum. From that, we can infer the intrinsic polonium rate and hence the bismuth rate. The key assumption in this strategy is that in this region, the polonium contamination in the fiducial volume is negligible, and this is confirmed by fluid dynamics simulation. Taking into account also systematic uncertainties on the bismuth uniformity in the fiducial volume, we can have the following constraint for the bismuth. Regarding dataset, it is more than 1,000 days of exposure, and we use the Monte Carlo modeling of the detector response. The cut on the data is made on muon and the daughter of muons, which is basically consisting in a time window in which we don't take data after the passing of a muon. There is also a fiducial volume cut, and also there is this technique called the threefold coincidence that is used to tag carbon-11 events. And also we took into account the radial distribution of the events that improve the disentanglement between external and internal contaminant. So then we can perform a multivariate fit in which we use the carbon-11 depleted spectrum and the carbon-11 enhanced spectrum, in which we use or not the TFC, the threefold coincidence, and also the radial information. We plug into this multivariate fit this constraint from for the PP neutrinos from beryllium, and then this is the results that we obtain for the interaction rate into the Xenon detector. It's 7.2 plus 2.9 minus 1.7 count per days per 100 ton of scintillator. Then we cross-check these results with a more simpler analysis, which is counting analysis, in which we choose a region of interest where we expect that the CNO, the ratio between CNO and background is maximized. We count the event into this region of interest, And then we subtract all the identified background. We extract the number of events per each background estimated by using the same constraint for PP and bismuth that has been used for the fit. And also for the other species we use the estimated number of events that comes from a reference analytical response model of the detector. Finally, to have we generate 10 to the 4 toy Monte Carlo realization, varying all the parameters related to the detector response and to the species rate, and determine the Sieno by subtraction of the background events. And the systematics are obtained as the width of the distribution of the Sieno rate. Here there are all the results from counting analysis and multivariate fit summarized. This red distribution is what we have from this sampling from the counting analysis. And also there is the log likelihood profile of the multivariate fit. And also for this constructing this profile, we took into account also systematic from fit configuration, bismuth shape, carbon level spectrum, and many others. And you see that the counting analysis and multivariate fit thus gives us compatible results, but the take-home message is that the no Sieno hypothesis is excluded at the 5 sigma significance. So finally, the final results of Sieno interaction rate in Boron is 7.2 plus 2.9 minus 1.8 count per days per 100 ton, taking into account statistical and systematic errors. This corresponds to a flux on the Sieno Neutrinos at Earth of 7 plus 2.9 minus 1.9 10 to the 8 neutrinos per centimeter square per second. And also, again, the no Sieno hypothesis is excluded at 5 sigma significance level. With this outcome, Boron has completely unraveled the two processes powering the sun, the PP chain and the Sieno cycle. Thank you for your attention.
Okay, thanks a lot, Riccardo, for the talk. I don't know, I don't see question. So I have one. Okay, there is one by Simone Rossoni. The observation of Sieno neutrinos could be useful for the study of the metallicity of the sun?
Yes, as you can see here, this cyan and pink band are the predicted rate for the low Z and the high Z models of the sun. And as you can see, with the precision that we have, we cannot discriminate between the two, but the result is closer to the high Z model. By high Z, I mean high metallicity. Sorry.
Okay, just very fast question that I start with the joke. So you spoke about a bang at the end of Boron. I hope this will be not a real bang, because in the underground lab is not safe. But can you give some anticipation on it or not? Or is there is
No, actually I don't know how is the situation by the politics point of view, of the bureaucratic point of view, about if Boron will be decommissioned by the end of the year. I think that everything was delayed for the coronavirus situation, and so probably we will at least take data until the end of the year and then start the decommissioning the next year. But I don't have any confirmed news about this.
Okay, another very quick answer to this question from Nina Burlak. Could Boron also study neutrinos from other stars?
I think not, because the flux goes down as the distance to the square. So the flux from, how to say, let's say if you take Proxima Centauri, it's 4 light years, and the flux will be basically 0 at Earth.
Okay, so thanks a lot also to Riccardo for the talk.
Thank you.
And so with this talk we we close the part of physics, and we go to the next part. So I ask Marco to introduce the prosecution of the TMS Day of Science. Thanks a lot.
Okay, actually, Luisa can take care of that. So please, Luisa, can you activate your camera and microphone and introduce our guests? Thank you.
So, good morning, everybody, to this chemistry session of the TMS Day of Science. I'm glad to introduce Professor Schroeder that will give his seminar. Professor Schroeder is at the head of the Targeted Drug Delivery and Personalized Medicine Group at the Xenon Israel Institute of Technology. His research is aimed at improving patients' quality of life and bettering their treatment by developing innovative medical technologies. Specifically, its research is focused on targeting metastatic cancer with nanotechnology and on constructing miniature medical devices that couple diagnosis to therapy, so theranostic devices. Today, he will talk us about novel drug delivery system. Please, Adi, when you want.
Can you hear me now?
Yes, yes.
Okay, can you see my screen, the presentation?
Yes.
Okay, great. So I want to thank you very much for the invitation. I'm really happy to be with everyone there. I can't see you, unfortunately. I can see only my own screen. So if there's something that goes wrong, please indicate. But these are Zoom days, so virtual days. So it's important that I get some feedback. If there's a question, please feel free. And as indicated, I come to you from Israel, specifically on the map, not very far from all of you. I think you're all located in Italy now, and so Israel is right here on the Mediterranean Sea, same sea. Israel is a beautiful country. For people who haven't visited, I want to encourage you to come. We're located in Haifa. Haifa is a city that sits on the Mediterranean Sea, about 1 hour north of Tel Aviv and an hour and a half by car north of Jerusalem. And as you know, Israel has, besides other sites, has many historical sites, Jerusalem and Nazareth and the Sea of Galilee and the Baha'i Gardens and a lot of nature that you can come and join, and of course science and technology. So that's about us, and the people that did the work, I only get to talk about it. This is my team at the Technion. I'm here in the center, and they're a group that I'm greatly inspired by, students from all different fields of science and engineering, and of course our funding bodies that help us a lot. So I'd like to start with what actually inspired me as a student when I came to study the field of nanotechnology and targeted drug delivery. I came across this paper. It was published by a physician named Harrington, and this physician looked at how nanoparticles, or the biodistribution of nanoparticles to tumors in patients. So the image you see in front of you includes 3 different patients. A patient on the top left-hand corner is with a tumor at the base of the tongue. This is a patient with breast cancer and metastasis in the local lymph node. And on the right-hand side, there's a patient with lung cancer and metastasis in the spine and in the bone marrow. Can you see my cursor on the screen?
Yes, we can see.
Okay, great. So 3 different patients, 3 different types of tumors, one more earlier tumor, one more advanced tumor. And despite that, they used nanotechnology to actually detect these tumors. So what you can see here in the image are nanoparticles that were injected intravenously into the vein of the arm. The nanoparticles circulate in the blood, and they actually target the tumor metastasis site. Now, each nanoparticle contains inside of it a contrast agent, such as indium-111 in the left image. And so what we can see here is the accumulation of nanoparticles in the tumor site. And of course, when you have that, you have less side effects to other regions in the body because the drug accumulates at the target site. And so this improves the therapeutic efficacy, reduces side effects. And the reason this happens is that the blood vessels in the tumor are actually different than the blood vessels we have in healthy tissues. So in healthy tissues, our blood vessels are highly regulated, and it means that they're like pipes, hoses, that the nanoparticles can hardly exit from the circulation into the healthy tissue. Contrarily, in sites of tumors, the blood vessels are actually formed in a very rapid manner, so the blood vessels are formed all the time. And instead of having well-aligned blood vessels, these blood vessels have small holes in them, actually nanopores in the endothelial layer, the layer that lines the blood vessel. And a nanoparticle here drawn as these white dots can actually extravasate, exit the blood vessel, and enter into the diseased tissue. So based on that phenomena alone, because the blood vessels are different in healthy tissue and in cancer tissue, nanoparticles can actually exit. And why nano? So the holes in the blood vessel and the wall of the blood vessel are about 200 or 300 nanometers in diameter, meaning that a particle smaller than that can exit from the circulation and enter the tumor. In fact, we know today that the size of about 100 nanometers is usually optimal for targeting cancer. And based on this phenomena alone, more than 80 nanomedicines have already been developed. The first was developed in Israel, in the Hebrew University, by my PhD advisor, Professor Yechezkel Baranholtz, and it's called Doxil. Doxil is a 100 nanometer liposome, which is a 100 nanometer particle that contains inside of it the anti-cancer drug doxorubicin. Doxorubicin is a very toxic chemotherapy. It has cardiotoxicity, can affect the heart, and because now instead of accumulating in the entire body, it actually targets the tumor once it's inside the nanoparticle, it had great advantages in the clinic and is still used for treating nearly 600,000 ovarian and breast cancer patients every year. But that's only one example. Last year, and these are just some examples of nanotechnology. Last year, Arikacide was approved. This is an antibiotic that's given through nanoparticles. It's inhaled by the patients, and it actually reduces extreme lung infections. By the way, it's also related today to some of the coronavirus patients. In a nanoparticle, you don't need to put only one medicine. You can put two medicines. Vixius is an example of a nanoparticle that contains a combination of two medications. And when you target two pathways inside cancer cells, you're much more efficient in targeting the disease. And 1.5 years ago was the approval of Onpattro. Onpattro is a whole new class of nanotechnologies. Here, it's instead of delivering a small molecule drug, they're actually delivering an RNA molecule, a molecule that contains a gene code inside of it. In fact, this specific gene code knocks down or stops the production of specific proteins inside the body. And when the regulatory bodies approved Onpattro, they mentioned how groundbreaking this technology is compared to any technology we had before. And they also indicated that without nanoparticles, you could not actually deliver such sophisticated and delicate medicines in a targeted manner. But we're in times of corona, and in times of corona, I think we should also mention the recent Moderna drug. I think everyone heard about this large clinical trial where nanoparticles again are used for delivering RNA. So on the left-hand side of this image is the nanoparticle Moderna is using. It's about 80 nanometers in diameter. It contains 2 to 6 strands of messenger RNA, which encode for proteins that will then be identified by the immune system of the patient in order to vaccinate against coronavirus. And you can notice that each one of these nanoparticles is very well engineered, carefully engineered, so that you have here you can see about 2 to 6 strands of messenger RNA, PEG lipids, which allow long circulation in the blood, and other components, other molecules that allow these particles to circulate in the blood and really reach their target site where they actually induce the therapeutic efficacy. So to maybe exemplify what a nanoparticle is, you can see this drawing here of a liposome. This is a lipid-based vesicle. It has an inner aqueous core where you can load drugs that are water-soluble. It has a lipid bilayer, and it has an outer surface of the system. Now, the size of the particle, usually when we talk about treating cancer or infections or inflammation, the particle size is usually around 100 nanometers in diameter. And there's a lot of engineering that goes into the lipid bilayer. For example, on the surface of the particles, you usually want to put molecules that can either target a specific tissue, so such as an antibody that would attach to specific tissues inside the body, or you want to put polyethylene glycol, PEG, as I showed you in the Moderna system, where you want these particles to circulate in the blood for longer periods of time. So either to avoid a tissue or to be taken up by a tissue. And more than that, the lipid bilayer itself, I always think of it as the door to a taxi. So you want to sit in the taxi comfortably when you're driving, such as when the particle is in the blood circulation. But when you reach the target site, such as you reach the university or the meeting you have, you want the door to open up, so the lipid bilayer to open up, and to allow the medicine from inside to be released so that it actually carries out the therapeutic efficacy. So there's a lot of engineering that goes into the formation of these nanoparticles so that they're active at their site. For example, several years ago, we invented nanoparticles that didn't contain any medicine inside. The nanoparticle itself was the medicine. And we use that for treating cartilage. Cartilage is the material we have in joints that allows us to run and climb and do daily activities. And there are patients that have a condition called osteoarthritis, where the cartilage inside their joints is degraded, and that causes inflammation in the site of the knee, for example, or the fingers. Very common illness. And what we invented are nanoparticles that are injected directly into the joint, and what they act there is as small lubricants, biolubricants that reduce the friction and wear inside the joint itself. So now, instead of the broken cartilage rubbing against the broken cartilage, the patient actually can regain their daily function, and by lubricating the joint itself. And when we tested this clinically, so we developed the technology, tested it in the laboratory, but then we went another step and we actually tested it also in patients, and we saw that our idea really worked in the patients. So our technology here in the blue lines actually was far better than the other drugs that are on the market for improving the daily function of patients, specifically allowing them to run and jump and climb up and down stairs. What was even more interesting is this small graph on the left-hand corner down here, is that when we tested how much pain medication these patients were consuming, are they still consuming the same amount of pain medication? We found that they were consuming about 1/4 the amount of pain medicine. So we had a good side effect instead of a bad side effect, because osteoarthritis, which is a chronic illness, of course, the patients need to take a lot of pain medicine many times, and that's not good for them. So now they were actually consuming a lot less pain medicine, so we actually had a good side effect. But I would want to go back with you, please, to the first image I showed you of the 3 different patients. So first, before I go on, can you hear me well?
Yes, we can hear you. Yes.
Okay, just making sure, you know, when I sit in a classroom or talk in a lecture hall, then I see the people here. Unfortunately, even though at heart I'd like to be with you, I'm here in my room.
Yes.
So I want to go back to the first image that I showed you, which was the 3 patients with the nanoparticles accumulating inside their tumors. And usually nanotechnology is used for delivering a medicine to a patient's tumor in order to improve the therapeutic efficacy, so bringing more medicine to the target site and less side effect. But we asked ourselves a different question. Could we use the nanoparticles not in order to deliver medicine, but in order to understand which medicine is best for each patient? Could the nanoparticle act as a small sensor that would give us an indication about which medicine is best for each patient? And just an example of how important this is a conference I attended several months ago before the corona, and the conference is all of medical doctors, breast cancer medical doctors, and they asked the different medical doctors how they should treat this specific patient. So I took a picture of the screen, and they give 4 options. So they indicate what the patient, indicate about the patient. This patient is a female. She's under the age of 50, and they indicate exactly what type of cancer she has. How should we treat her? Now, I, as an engineer, was sure that there'd be an answer that would be very clear to the medical doctors, and I was very surprised to see that when they voted, actually, there was a full distribution between how to treat this specific patient. Meaning, if you go to doctors that vote for number 1, or for number 2, you get a totally different treatment. And that worried me very much, because it means that we don't have good tools for deciding which treatment is best for each patient. And just to calm the medical doctors there down, they showed actually the data from another conference that asked the same question. And they showed how there the medical doctors voted. And notice that in the other conference, 42% voted for option number 1. While in this conference, only 27% voted for that. And I would say more worrisome is that a quarter of the doctors that voted for number 3 in the first conference, while only 10% in the other large conference that attended. So also between doctors to doctors, there's great disagreement how one should treat in the best manner, and we lack tools. So we asked ourselves, could nanotechnology help here? Could we use nanoparticles in order to indicate which treatment will be best for each patient? And what we did is, instead of taking all our nanoparticles and loading them with the same medication, we actually took the nanoparticles and loaded a different medicine into each nanoparticle. So each nanoparticle has now a different medicine inside of it. And more than that, because the nanoparticles are, we didn't want to have too much medicine in each nanoparticle, we actually loaded a very low dose into each one of these nanoparticles, a low dose of the drug that was so low that we couldn't use any of our tools in the lab to measure which medicine we have inside. So what we did is we added a DNA barcode into each one of the nanoparticles, and now the DNA barcode tells us which medicine we loaded into each one of these nanoparticles. So we create a cocktail of nanoparticles. Each nanoparticle has a different medication inside of it. We inject the nanoparticles intravenously. They circulate in the blood. This takes about 24 hours, and then they reach the tumor site through the leaky blood vessels that I showed you earlier on. Inside the tumor, the nanoparticles distribute to the different cancer cells, and then we wait another 24 hours. Some of the barcoded nanoparticles kill the cancer cells, and others don't. So what we do is we take a biopsy from the tumor, and we look at the different cells coming out of this biopsy. Some of these cells are alive, and some of these cells are dead. The live cells contain barcodes of medicines that are not effective, and the dead cells coming out of the biopsy contain barcodes of medicines that are effective. So that was our approach to testing the activity. So what does it look like? Does it actually work? So the answer is yes. So first, we looked and we saw the accumulation of the nanoparticles. Here, these are the red region are the nanoparticles accumulating inside the tumor cells. The blue are the nucleus, the nuclei of the cancer cells, and the red are the nanoparticles inside. Or more clearly, here you can see a single triple-negative breast cancer cell. It looks a little bit like a ghost. The blue inside the cell is the nucleus, and the green dots you can see here are the barcodes that the nanoparticles carried into the cell. And just so people that aren't familiar with cancer cells, a cancer cell usually is not round. If it's round, it means it's dying. That's a good thing. Cancer cells usually have, it looks like almost arms and legs because they constantly move and grow and propagate, which of course isn't good for us. So what does the readout look like? So when we take out the biopsy from the patients, we get a panel, and the panel includes dead cells and live cells. The upper panel here includes the dead cells, and you can notice that the blue barcodes coming out of the dead cells are more abundant. We have more of them than the blue barcodes we have in the live cells. The blue barcode here is a drug called gemcitabine, meaning that we have more dead cells that have gemcitabine inside of them compared to live cells. But this is just an example. And when we looked at the data for all the cells inside the tumor, we saw, for example, that for each 5 dead cells that had a barcode of a drug called cisplatin, we had only 1 live cell. So 5 dead cells for each 1 live cell. So that looked great. But then when we went on to gemcitabine, a different medicine, we saw that for each 6,500 dead cells, we had only 1 live cell. So we actually could rank the different medications based on the dead cells to live cells ratio, or we rank the potency, the patient-specific potency of the medicine. And we know that medicines actually act differently in each patient. So here you can actually create the right dose for each patient in order to give them the right medicine that will be most effective for them. We went on and we tested if our prediction works. This is in mice. What we saw is that when we treated with gemcitabine, which was our prediction, the tumors were smaller compared to when we treated with doxorubicin, where the tumors were larger. The mice lived longer when we treated with gemcitabine. And more than that, when we looked inside the tumor itself, we also saw that the tumors that were treated according to our prediction, according to the best medicine, tumors were in remission, meaning that they're dying away. While when we treated against the prediction, these tumors were very, very lively and progressing, which of course is not good. So we were happy with that data. And we went on, and because of the time, I won't go deep into that, but I would like to just indicate 2 things. That a cancer tumor is usually built about 50% of cancer cells and 50% of helper cells, other cells that help the cancer actually to continue growing. And in some cases, you want not only to destroy the cancer cells, you also want to destroy the helper cells. But the helper cells may be responsive to a different medicine than the cancer cells. And our technology actually allows, using the barcoded nanoparticles, you can actually indicate how different cell types inside the tumor respond to medication. For example, the cancer stem cells may respond to one medicine, while the cancer cells might respond to a different medication. In addition, one thing we found that actually troubled us a little bit is that the primary tumor, meaning the original site of the tumor, and the metastasis, which are the distant dissemination of cancer to other sites in the body, sometimes respond to different medicines. And this is actually very problematic because if the primary tumor responds to one medicine and the metastasis responds to a different medicine, it means we may have to give 2 medications, or maybe use one technology such as surgery to take out the primary tumor, the large tumor, and maybe treat the metastasis using nanotechnology and nanoparticles. So that's what this technology actually allows. So barcoded nanoparticles actually allow you to understand how different cells or different tumor cells in different regions of the body, either the primary tumor or the metastasis, how they respond to medication and which medication is best for treating each patient's tumor, understanding that different patients respond to different medications. So just to wrap this up, is an animation of the bar-coded nanoparticles injected intravenously. They enter the tumor through the leaky blood vessels, and then the bar-coded nanoparticles distribute between the different cells we have inside the tumor. And at that point, we can actually get a readout which medicine worked and which medicine didn't work. So for the last 5 minutes of my talk, I would like to discuss a totally different field in regards to elephants and nanotechnology. So again, using nanoparticles to deliver materials to tumors. But in this case, it came through an interesting discovery that collaborators of us have been working on. So the first phenomena that actually is extremely exciting is that elephants don't get cancer. Elephants, these large animals that weigh more than 100 times more than we do, large creatures, they live 70 or 80 years and they don't get cancer or hardly get any cancer at all. And this question has been a scientific question for many, many years. And this is a nice review that was published several years ago asking that question, how can it be? They must have a mechanism that protects them that we lack. And collaborators of ours, Dr. Joshua Schiffman on the right-hand side here, and myself looked into this phenomena. And actually, Josh started this study slightly before we joined in, and we added the nanotechnology aspect. And Josh looked at the biology aspect, and today we work together. So Dr. Joshua Schiffman looked into the cells of elephants and to human cells, compared them, and looked what's different between elephants and our cells when we look at cancer pathways. And what he discovered is that there's one gene that's very, very different between humans and elephants, and it's connected to cancer. This gene is called P53. And it's missing in half of human tumors. It's considered to be like the police car in every one of our cells that protects the cell from becoming cancerous. So if a cancer cell wants to become cancer, it kicks out the police, and it actually deactivates the P53 inside the cell. Unfortunately, as we age, we have less P53 in our cells, and that allows actually an incline or an increase in cancer. And just to explain how important this gene is for cancer is that healthy adults have 2 copies of P53 in each one of our cells, so 2 police cars. And unfortunately, there are children that are born with a syndrome called Li-Fraumeni syndrome. They have only 1 P53 gene inside their cells. And they have 100%, these kids have 100% risk of getting cancer, meaning they all get cancer because they're missing the P53 gene inside of their cells. So it's not a question if they get cancer. For these unfortunate children, it's a question when will they get cancer. And it's all because they're missing 1 gene of P53 in each one of their cells. When we look at elephants, if we have 2 copies of P53, elephants have 40 copies of P53 in each one of their cells, which is phenomenal. And in fact, when you look carefully at the cells of the elephant, you see that the first 2 copies of P53 are identical between the humans and the elephant. And the last 38 copies are small alterations, small mutations of the elephant P53 compared to ours. And what we did in the lab is we studied the different P53 genes, and we found one of them that is extremely active in preventing cancer. And what we did is, what we know how to do is, we loaded the elephant P53 gene into nanoparticles, and we tested its activity on cancer cells. So we're putting the elephant gene now into human cancer cells. So on the left-hand side, you can see osteosarcoma cells. These are cells, cancer of the bone, without the elephant gene. And on the right-hand side, with the elephant gene. And I already told you that when cancer cells become round and small, it means that they're dying. So you can notice that on the right-hand side, the screen is almost all dark. And on the left-hand side, you see only the dots of the dying cells. On the left-hand side, you can actually see the cancer cells that are progressing because they don't have the elephant gene inside. So what we did is we delivered the elephant gene to the cancer cells. This is a close-up image. You can see here, this is a prostate cancer cell. And boom, you can see the moment of explosion. Again, you see the moment of explosion. I hope also on your screen you could see that. Could you see when the cell exploded?
Yes.
Okay, thank you. Just making sure. Another example of the cell exploding here, again on the right-hand side, this is pancreatic cancer. Boom, you can notice the cancer cell actually exploding when you add the elephant gene inside. Again, take a look at it again. Right now, that's the moment of death. And on the left-hand side, look how many cells. The cells are all alive and very active. So what we did is just by delivering the elephant gene into the cell, you actually activate, you bring back the police, and that actually stops the cancer cell from continuing growing. So I'll end here just by saying that we've tested this technology already in more than 15 different types of cancers, and we're working on developing this as a medication. And I'd like to end by saying, just looking at what we discussed today. So we discussed three things. The last point, sorry, is not relevant. The first point is that I showed you that liposomes can be biomaterials for treating osteoarthritis, so they were lubricants. The second point is that bar-coded nanoparticles can be used for predicting which medicine is best for treating a cancer patient. The last point that I have here, I didn't have time, so I jumped over it, but I did try to show you that nanotechnology can be used to deliver an elephant gene into human cancer cells. And most important for me to say is that nanotechnology is already a reality in the clinic and can be used for helping to treat cancer patients. So I want to thank you very much for this opportunity to speak to you today, and I hope that was of interest.
Thank you, Avi, for this very interesting lecture. Really exciting for me. There are some questions from the chat. The first one, two questions. I have two questions. For the treatment of arthritis with lubricating nanoparticles, how long does each dose last? For example, how many injections would they need over the course of a year? The second question, for the personalized medicine, do you always directly administer the nanoparticle to the patient, or would you ever take a patient sample first and administer the nanoparticle in vitro to have an idea of which drug are effective?
Yeah, so thank you. Those are two great questions. Thank you very much. Regarding the osteoarthritis, what we tested is every 3 months we gave the patients an injection, and what we saw is that usually once every 3 months, so 4 injections a year should be enough. Again, it varies from patient to patient. There's some patients that their cartilage is in such bad condition that they may need to come more often, and other patients maybe 1 or 2 injections a year would be enough. It doesn't cure the osteoarthritis, it's important for me to say, but what it does do, which is very, very important, is that once you allow the joint to work better, you exercise the joint, then usually you start seeing a natural curing of the cartilage and better curing of the bone underneath it. So that's one aspect. Regarding the personalized medicine, so why do it in the patient and not do it in a dish? Very good question. And the first answer is actually the time. So using our technology, which uses about 1/1000 the therapeutic dose, so a very, very low dose, you get a readout within less than 1 week which treatment to give. In fact, within 3 days, you already know which treatment to give. When you do it in a dish, it usually takes a month to 2 months to get the readout. Now, another aspect is that the cells respond differently inside the body and outside the body. And when we have the context of the body, we actually get a more accurate readout about which medicine is best. And the third aspect is actually looking at different points in the tumor and also metastasis. So because the nanoparticles go to the entire tumor that's accessible and also to the metastasis, you can actually take your readout from also the metastatic cells and also from the tumor cells, and that sometimes gives you an advantage. I do agree with the question that says that, but doing it in a dish may be less invasive. That is true, because you don't need to do a second biopsy, or you don't need to do a biopsy. Here we do only one biopsy. So I think there are advantages maybe to both approaches.
Okay, thank you for your answer. There are other two questions. One from Marco. In our lab, we study extracellular vesicle exosome, and we notice a specificity of targeting. For example, tend to go back to bone. Can you tell us how you or other colleagues are exploiting this feature to engineer better targeted drug nanoparticles?
So I would say that extracellular vesicles are the next step of nanotechnology, because extracellular vesicles are the natural mean for communicating between cells. And I would say that it's very interesting, and we see more and more papers about that. Better engineering our nanoparticles so they're more like the extracellular vesicles, so you improve the targeting, such as adding proteins on the surface and sugars. And so I have to say that when I entered the field of nanotechnology, the field of extracellular vesicles didn't exist. We didn't know this amazing phenomena of extracellular vesicles. And today, when I look at it, I say that extracellular vesicles are the natural way of nanotechnology. So I have to say it's amazing. And I always, every paper I see that comes out is very exciting to see how nature does it, and to learn from nature maybe how to improve our nanoparticles.
Thank you. Another question, are there liposome technologies to target a small percentage of cells that can survive therapies and generate tumor relapse, such as treatment-resistant cell or tumor stem-like cells?
So I think that's exactly where we're aiming to improve the system so that it also treats resistance. And I'll just give one example, not work that was done by us, but work that was done by other people. And I had a small contribution, is that people have been doing now co-delivery of siRNA to knock down a resistant pathway together with a small molecule drug or a drug. So you use the nanotechnology to knock down the pathway so the resistance is suppressed, and then you deliver with nanotechnology in the same nanoparticle, you also deliver the medicine that previously the cell was actually resistant to. So I will say that nanotechnology is entering that area very much.
Okay, the last question. In some cancer, the PT53 is mutated. When you use the elephant PT53, you kill most of the tumor cells. But what about the ones that survive? Did you check whether the elephant PT53 undergo mutation?
Yeah, that's a very good question. We haven't tested that yet. And I think one way to overcome that is by delivering several doses of the elephant P53. And but I agree that one of our biggest problems is what happens when we have cells left over in the tumor that we don't treat. Of course, there is an achievement by first killing the first round, but sometimes we do that through several treatments. Just like with antibiotics, that you give several doses until the bacteria is down. And also with cancer and nanotechnology, a single injection usually isn't enough. So you have to give a second injection. And if the mechanism of the cell can deactivate the elephant P53, we have not seen that yet happen because the elephant P53 is actually more stable against mutations. That's one of its advantages. But if that does happen, then maybe that technology alone would not be enough. And I think in many cases we see that you need a combination of technology, meaning giving one medicine together maybe with the P53, And I would also ask, could we also maybe use the P53 as a preventative medicine, a treatment that would prevent cells from becoming cancerous, because technically we have P53 in all our cells, and if it's functioning well, it shouldn't harm healthy cells, but it should harm the cancer cells.
So, thank you, Avi, for your answer, and most of all for your interesting talk. Thank you for being with us. We are a little late, so we skipped to the other presentation of this chemistry session, and it is about Elena Allegritti, that is a student of our course in chemistry at the Department of Physical and Chemical Science, and she will talk about liposome to deliver levodopa in the treatment of Parkinson's disease.
Oh wow, that's very interesting. So I'm gonna mute my camera and that, but I will listen. So thank you very much for having me today.
Thank you again. Please, Elena, when you want.
Okay. Can you see my presentation?
Yes.
Okay. So good morning, everyone. First of all, I would like to thank the scientific committee for giving me the opportunity to show my work today, which is about liposomes as potential drug carriers for levodopa. So Parkinson's disease is a progressive neurological disorder that affects the brain cells that produce dopamine, causing movement disorders. After diagnosis, treatments can only help to relieve symptoms, but there is no cure. The administration of dopamine itself is ineffective because it cannot cross the blood-brain barrier, while levodopa, which is an intermediate in dopamine synthesis, can cross the blood-brain barrier, but only a small amount of the drug can reach the brain. So it must be administered in large amount, causing side effects. Furthermore, levodopa is easily oxidized in aqueous media following the reaction, and we can see its oxidation in time. But it is today it is the most effective drug to treat the Parkinson's disease. So a suitable drug delivery system that can increase its concentration into the brain, that can protect it from the oxidation reaction, is needed. Liposomes, which are sphere-shaped vesicles consisting of one or more phospholipid bilayer, are attractive drug delivery systems due to their biocompatibility and their capacity to entrap both lipophilic and hydrophilic compounds. Furthermore, their surface can be functionalized in order to target specific sites, and based on the formulation, the preparation technique, liposomes can be obtained in a large range of sizes and morphologies. So we prepared 8 different formulations in order to vehiculate levodopa. Each formulation contains an extract, a mixture of phospholipids extracted from egg yolk, cholesterol, and one synthetic surfactant. The synthetic surfactant we chose show the N-oxide or the quaternary ammonium moiety, and they differ for the polar head group and the chain length. In particular, literature reports that the N-oxide surfactant can enhance the antioxidant properties of the molecules included in the aggregate they form. And since we need an antioxidant in order to prevent levodopa oxidation, we chose these synthetic surfactants. The antioxidants we chose are L-ascorbic acid or quercetin. L-ascorbic acid is hydrophilic, so it will be located in the aqueous phase of liposomes together with levodopa, while quercetin is hydrophobic, so it will be located in the lipid bilayer. So here is the investigation of the influence of the synthetic surfactant structure and the preparation technique on the final properties of the aggregates. First of all, we prepared levodopa and L-ascorbic acid loaded liposomes by thin film hydration methodology, followed by extrusion. All samples show high homogeneity and a mean size of 150 nanometer, and they are stable for at least 1 week. We evaluated the entrapment efficiency of levodopa and L-ascorbic acid, and as we can see, all the formulations containing the C14 surfactant lead to the highest entrapment efficiency. Then we prepared the same formulation by reverse phase evaporation methodology, and compared to the previous technique, it has the advantage of higher internal aqueous loading, meaning an higher entrapment efficiency of hydrophilic molecule. Even in this case, we evaluated the entrapment efficiency of levodopa and L-ascorbic acid, and as expected, we obtain a higher entrapment efficiency of the drug and antioxidant. And even in this case, the formulation containing the C14 surfactant leads to the highest entrapment efficiency. The entrapment efficiency of the drug is always higher than the ascorbic acid, because the antioxidant get consumed in order to prevent the levodopa oxidation. Then we evaluated quercetin loaded liposomes, and since this is a preliminary work, and since we used the passive loading, we didn't evaluate the entrapment efficiency of levodopa, since we didn't expect a large variation of the amount of the drugs entrapped in liposomes, but we only evaluated the entrapment efficiency of quercetin, and as you can see, all the values are very high. Of course, then we will evaluate the entrapment efficiency of both quercetin and levodopa. Then we evaluated the antioxidant activity of free quercetin and when quercetin is in liposomes, following a protocol which is present in literature, and it is based on the ABTS properties. The ABTS molecule can be easily oxidized into ABTS radical cation, which confers to the solution a green color. When the ABTS radical cation reacts with an antioxidant, quercetin in this case, it is reduced to ABTS, causing the discoloration of the solution that can be followed by UV measurements. Of course, the faster is the ABTS reduction, the higher will be the quercetin antioxidant activity. So in black, we can see the reduction of ABTS radical cation alone. And as we can see, when quercetin is included in liposomes containing the 30% of cholesterol, there is an effect on the ABTS radical cation reduction. Probably quercetin is located in the inner region of the lipid bilayer, so it cannot interact with the ABTS radical cation. While quercetin is included in the formulations containing less cholesterol, the ABTS restoration is faster than in the case of the ABTS radical cation alone. So in this case, probably quercetin is located near the head group of the bilayer, or maybe the bilayer is less rigid, so the antioxidant can interact with the ABTS radical cation. So in conclusion, we entrapped levodopa in mixed liposomes together with L-ascorbic acid or quercetin with thin film hydration methodology or reverse phase evaporation methodology. And as expected, reverse phase evaporation methodology leads to the highest entrapment efficiency. Liposome composition does not affect the entrapment efficiency of the drug and the antioxidant, but it affects the location of quercetin in the lipid bilayer and the antioxidant activity of quercetin when included in liposomes. I would like to thank all the researchers that worked with me on this investigation, Professor Luisa Gianzanti, Dr. Sara Baptiste, and Dr. Maria Maggi from University of L'Aquila, and Professor Maria Luisa González Rodriguez from University of Seville, and all of you for your kind attention.
Thank you, Elena, for this presentation. There is a question from Marco. Quercetin is used in association with dasatinib as a senolytic. I test a drug that reduces the number of senescent cells, leaving the tissue younger. Did you think associating that with dasatinib and delivering it in cells?
Okay, I can understand the question because I didn't hear the question.
Okay, you can read it
Okay.
from the chat. It's about the possibility to deliver quercetin together with another drug to cells. Dasatinib.
Okay. Yes, I think it could be possible to do it. So.
Okay. Thank you, Elena, for your presentation. If there are no other questions, we keep to the other speaker because we are a little late. Thank you, Elena. So the other speaker is Vincenzo Marzicano. That is okay. Camera. Okay. Vincenzo Marzicano, that is a PhD student at the Department of Physical and Chemical Science at the University of L'Aquila, and will talk us about gold-catalyzed regioselective functionalization of thalidomide-protected propargylamines, an easy way to access valuable chemicals. Please, Vincenzo, when you want, you can start.
Yes. Good morning, everybody. Thanks, Luisa, for the presentation. Can you see the screen?
Yes.
Okay. So, today I will speak a little bit about gold catalysis. Gold is probably one of the first metals that have been discovered by mankind and has always been used mostly in the preparation of precious objects such as jewels and money, but also has been used in industry thanks to its conductivity properties in the manufacturing of electronic compounds, and also in medicine and dentistry. But only recently it has been discovered that gold can be used very efficiently in chemistry, especially as catalyst. In catalysis, gold is mostly used in two oxidation forms, gold 1 and gold 3. And in general, what is used are organogold compounds. That means that gold is linked with organic ligands, such the ones that are presented here, that are used mostly to modulate gold reactivity and also to improve the solubility in organic solvents. But why gold is so useful as a catalyst, especially in activating pi bond containing compounds? This is mostly linked to relativistic effects. Relativistic effects are effects of quantum mechanics that are linked to the speed of the rotation of electrons that reach a peak with gold. And without going into deep, these relativistic effects cause a change of energy of the frontier orbitals of gold. The frontier orbitals for an atom are the orbitals that are mostly involved in the reaction and in reactivity, and this for gold causes a strong pi-Lusic acidity, but at the same time a high tendency to stabilize carbocations and a low tendency to undergo oxidative additions and reductive eliminations that are reactions very common for metals. All these characteristics cause the cause of the ability of gold to activate alkynes or alkenes, the compounds bearing pi bonds, towards reactions that are not commonly that are not common for these compounds, such as nucleophilic additions. Gold, in fact, thanks to its ability to accept pi electrons, is able to increase the electrophilicity of alkynes that are, on the contrary, mostly considered as nucleophiles. And as you can see from the catalytic cycle on the right side of the screen, this enables the anti-addition of nucleophiles. Nucleophiles that could be of different nature, but what I want to stress in this presentation is water as nucleophile. In fact, when water is added to alkyne, we have a reaction that's called hydration. The hydration of alkynes is a very important reaction because it yields carbonylic compounds that are very useful in organic synthesis. Historically, this reaction has been performed with mercury salts, but as you may know, mercury is highly toxic both for environment and humans. And gold has emerged as a valuable alternative because it catalyzes this reaction at much milder conditions, with shorter reaction times and with higher degrees of regioselectivity. In fact, when hydrating unsymmetrical internal alkynes, two different carbonyl compounds can be obtained, and gold seems to have better performances in terms of regioselectivity. It means that one of the two possible products are obtained as the major component of the reaction mixture. We decided to perform our hydration reaction of propargyl amines that are alkynes very interesting because they bear proximal to the triple bond an amino group, are very useful as organic scaffolds, and when submitted to hydration they can yield two different compounds, beta aminoketones or alpha aminoketones, that are very interesting, especially beta aminoketones, because the beta aminoketone moiety is a widespread moiety in drugs, for example, bupropion or other drugs like that. In literature, there are only a few reports of hydration of propargyl amines with gold. All the reports are with gold 3. And in all the cases already reported, the amino group was linked to a protecting group that was useful to direct the regioselectivity to obtain only the beta aminoketone derivative. But the problem is that this protecting group cannot be easily removed afterwards, and this prevent the further use of the beta aminoketone generated in other types of reaction. So we wanted to bypass this drawback, and we decided to perform our reactions using the compound 1A, that is the N-propargyl phthalimido derivative, using phthalimido as a protecting group. But why phthalimido? This is mostly because obviously the reaction performed on the unprotected derivative was not successful, and this was the first reason why we decided to use a protecting group. But of course, the phthalimido moiety is better than the other protecting groups reported in literature because it can be very easily removed, as you can see, at room temperature with high yields, generating the beta aminoketone with the free amino group. And also because the phthalimido moiety is widespread in pharmaceutical compounds, for example, thalidomide. So this means that the library of compounds we were to synthesize may have a pharmaceutical application, plausible pharmaceutical application, even without the removal of the phthalimido moiety. So we went through optimization of reaction conditions very rapidly. We identified the best reaction conditions, and with this optimized reaction conditions, we synthesized a panel of compounds. This is mostly done in organic chemistry in order to demonstrate that the methodology is versatile, so it's compatible with different types of substituents, as you can see here, aromatic, heteroaromatic, alkylic, and this to demonstrate that our methodology is very versatile. We decided we wanted to further improve our methodology. In fact, it is known in literature that by adding additives to the reaction conditions used for hydration, and different types of reaction can be performed at the same time, what has been called functionalized hydration. It means that at the same time the alkyne undergoes hydration and the formation of other carbon heteroatom bonds, and we were particularly interested in carbon fluoride bonds because these bonds are very sought in organic chemistry because fluoride containing molecules are have interesting pharmaceutical properties, and so we wanted to achieve this by using select fluor as an additive. That's a molecule that you can see on this slide that is non-toxic, stable, very easy to use in laboratory. So by adding select fluor at our reaction system, we were able to obtain 3 different compounds from the same starting material: the alpha monofluoride derivative, the alpha difluoride derivative, and the diketone derivative. At the beginning, we obtained all the 3 together, but fortunately, we were able to, by changing temperature, equivalence of select fluors, the type of gold catalyst and solvents, we were able to find reaction conditions that enable to selectively obtain only one of the 3 possible derivatives. And this is very important because in organic chemistry, something that's very useful is the possibility to obtain different compounds from the same starting material. This in fact enable to reduce a lot the difficulties of the drawbacks in organic reactions. This is something that's still ongoing, so this is only the preliminary results of our substrate scope, but also in this case this substrate scope shows that our methodology is very versatile also when adding select fluor. So in conclusion, we were able to successfully perform hydration reaction on N-propargyl phthalimides by using gold catalysis, and differently from what has already been reported in literature, the phthalimido-protecting group could be easily removed, so generating the beta aminoketones derivative that are very important. And we were also able to further increase the number of derivatives that could be obtained by us by simply adding or changing some aspects of our reaction conditions. And that's it. Thank you for your kind attention.
Thank you, Vincenzo, for your presentation. We have a question from Valeria Nori. Are gold catalysts much more expensive in comparison to other transition metals catalysts?
Well, when thinking about gold, someone may think that gold is quite expensive. In reality, the gold chloride, that's in mostly cases the starting point for the synthesis of all the other catalysts, is it's not much more expensive than other catalysts, for example, palladium or platinum. For example, for platinum or rhodium, the cost of the gold starting material is lower. Of course, in comparison to other type of catalytic systems, it may be a little bit more expensive, but of course, gold catalysts are used at very low loading. Generally, we can also go by using. We can also use gold as ppm concentrations, and so yes, it may be expensive, but of course the quantities used in laboratory are very low. So,
okay, thank you for your presentation and for this answer. We can skip to the other speaker. The last speaker of this chemistry session, but it's another PhD student of our Department of Physical and Chemical Science, Valeria Nori, and will tell us about her investigation that carried out at the department in L'Aquila and at Cardiff University. In particular, she will talk us about triaryl-borane catalyzed amination reaction, a novel metal-free approach. Please, Valeria, when you want, you can start.
Good morning, everyone. Could you see my screen?
Yes.
Okay. So, good morning, and thank you, Lisa, for the introduction. So, let's start our journey with boron-based catalysis. Today, I'm going to talk about concept of catalysis and 3 projects that follow during the first 1.5 years of my PhD. So metal catalysis, in particular palladium catalysis, and main group Lewis acid catalysis, in particular boron catalysis, and then asymmetric boron-based catalysis. So what is a catalyst? A catalyst is a substance that will increase the rate of a reaction by providing an alternative reaction pathway with a lower activation energy, as this scheme shows. There are two different types of catalysis, the homogeneous one and the heterogeneous one. The homogeneous catalysis refers to reactions in which reactant and catalyst are in the same phase. On the contrary, the heterogeneous catalysis refers to reaction in which reactants and catalysts are in different phases. We know that there are several kinds of catalysis according to the nature of the catalyst itself. So metal catalysis is the one that Vincenzo showed you, in particular gold catalysis in this case. But we have the catalyst which is a metal, like silver, transition metal, like silver, palladium, gold, and so on. Organocatalysis, it's like catalysis with organic molecules. Biocatalysis, which is when the catalyst is an enzyme, and the photocatalysis, which exploit light as catalyst. But today we start with the first project that I followed during my PhD, which is based on metal catalysis, and in particular it's based on palladium catalysis. This project is about cyclocarbopalladation followed by Suzuki-Miyaura coupling reaction of substituted propyl amides with aryl boronic acids, which can give us really interesting pharmacological molecules like isoquinolinones. In this project, you can see that the first step of the synthesis is the oxidative addition of palladium to the amide. So we have the formation of the intermediate He1. Then after that, the cyclocarbopalladation give us the vinyl palladium intermediate, and the boron acts in this part of the project when we have the transmetallation of the nucleophilic group from boron to palladium, and then the formation of the products and the release of the catalyst itself. The first thing to do in this project was to optimize the reaction condition. So I changed several solvents, temperatures, the ratio between the propylamide and the boronic acid, several catalysts, and I found the best one. So the reaction, which was carried out in ethanol at 80 degrees in a ratio of the amide and the aryl boronic acid of 1.5, and with the palladium dichloride as the catalyst. This reaction gives us the product with an excellent yield of 90%. Here follows the substrate scope. So all the molecules that I synthesized following this procedure, changing the substituents on the propylamide or on the aryl boronic acids. The second project that I want to show you, which involves a different type of catalysis, is boron-based catalysis. This is part of the work that I did in Cardiff University under the supervision of Rebecca Mellon, who is a young chemist working on main group catalysis, in particular on boron catalysis, and the application of the catalyst that they synthesize in organic synthesis, and mechanistic studies to determine the role of the Lewis acid itself are carried out. Why it's so important to work with the main group Lewis acid catalysis? Because these kind of elements of the periodic table are really abundant. You can use mild reaction condition, and you can avoid all the toxicity which is linked to metals. But how a Lewis acid catalyst works? So in particular, I work with boron and with the BCF, which is a particular type of catalyst, Lewis acid, because it has a empty p orbital on the central boron atom, who can accept the electron pair from donor molecules. It is used as co-catalyst in polymerization of reaction of olefins, and it's used as a catalyst for organic reactions, and it's used in the FLP chemistry, the first release pair chemistry. So the project that I followed and I want to show you, it's about an alternative boron-catalyzed CN bond formation, so CN cross-coupling products, which give us the products in using lower temperature and milder reaction condition. In fact, no hydrogen gas or silane reductants are used, avoiding metal toxicity and giving us products which are really easy to purify. These molecules are so interesting to synthesize because amine compounds are present in a lot of bioactive molecules such as natural products, pharmaceuticals, and agrochemicals. I want to show you how these catalysts can catalyze the reaction itself. So first of all, we have the coordination of the boron to the ester. It follows the elongation of the CO bond, the bond cleavage, the CO bond cleavage, and the generation of the electrophilic carbanium ion. After that, the nucleophilic attack of the amine on the nucleophilic carbanium ion occurs. We have the deprotonation of the intermedium A3 formed, the release of the catalyst, and the formation of the product that we want to obtain. So the catalyst generates the electrophilic carbanium ion, and then this electrophilic carbanium ion is attacked by the amine to interesting molecule. Oops.
Okay.
Can you hear me?
Yes, now yes.
Okay. So we found the best reaction condition, and then, as I showed you before,
we don't see the screen.
Okay. I don't know why. Let's see. Can you see it now? Can you see the screen now?
Yes. Yes.
So we optimize the reaction condition, and then it followed the substrate scope. It's a huge substrate scope, changing all the amine part and the ester part of the reaction. You can see that we obtain a lot of products using desubstituted diphenyl amine and aniline, carbazole, substituted carbazole, indole, and pyrrole. And so what I want to underline is, little by little, I started from a really well-known reaction, which is the Zucchini-Aura reaction, when boron is important because it makes the transmetallation of the nucleophilic group from the boron to palladium. Then I work in Cardiff on the boron catalysis, and now under the supervision of the Professor Armando Carlone, I'm working on the synthesis of a catalyst, which is a boron-based catalyst, to obtain asymmetric catalysis with boron. Thank you for your attention, and thank you to the TMS committee for inviting me and select my presentation.
Thank you, Valeria, for your presentation. There is a question for you. I know that boron is quite sensitive to air and moisture and difficult to handle in laboratory. Have you had problems in this sense, and how have you overcome them?
Yes, so boron catalysis is really air sensitive. This is why when you are when you perform boron catalysis, you have to use a globe box, which is like a box with gloves full of nitrogen, and you can perform your sample preparation in it. So yeah, this is a problem of boron catalysis, but you can easily undergo this problem using the globe box.
Globe box, okay. Thank you again, Valeria. I would like to thank all the speakers of this chemistry session. And we are a little late, so we can skip to the biology session. That will be chaired by Professor Annotetti.
Okay, thank you. I think that we can continue with the next session on biology. And I have the pleasure to introduce you Professor Karl Kadler. He has a PhD in medical biophysics. He obtained a PhD at the University of Manchester. He has been postdoctoral fellow at the Jefferson University in Philadelphia. And at present he is professor of biochemistry at the University of Manchester. He is also director of the Wellcome Trust Center for Cell Matrix Research and the director of Research Cellular and Development System in Manchester. Karl is expert in extracellular matrix biology, especially collagens and fibrosis. Particularly interested in the circadian rhythm in the extracellular matrix proteins, especially in tendons. And today he will talk about circadian clock, collagen, and the search of antifibrotics. So, Karl, please.
Thank you. Can you hear me, firstly? Can you hear me, Anna?
Yes.
Firstly, I just want to say hello. It's so nice to see you again. I haven't seen you for a little while, so I hope that you are well. I'm going to try and just share my desktop if I can. Can you see my presentation there? You can see it. Yes, we can see
and we can hear you well.
Perfectly. I think this is my first time using Microsoft Teams, and it's a bit of a learning curve. So I have to thank Fabiana and Marco, who I met up with on Monday, and they've talked me through how to use the software. So thank you. A special thank you to them. Okay. If my internet fails, or if you can't hear me, just please tell me, and I will do my best to recover it. Okay. So let me just start. First of all, thank you for inviting me. It's a pleasure to be a part of your Science Day, and I realise that this is a switch of gear from physics to chemistry to biology. So I thought I would try and keep it as simple as I can, and just please let me know if it's too complicated or if I go too quickly. Okay, so I'm going to say a little bit about the circadian clock, collagen, and the search for antifibrotics. Let me see if I can go next slide. Let me start by just thanking a few people in the lab. I'll try and mention their names when I go through my presentation. The list of people in my lab is listed here, and I hope that you can see my mouse moving. Here, I'm going to talk about the work that these people are doing. Chris is a new addition to the lab, and he's a postdoc who just started. He's taking over the work that Ben has started, so it's a pleasure to welcome Chris. And I'll try and mention a few people who have contributed to the work in the past. Large list of collaborators on my right-hand side, and funding predominantly from Wellcome Trust, recently from BBSRC, very generous funding that we just received from them. So we have funding through to 2025, which we're very happy about. And of course, working with Anna, we just concluded a Rubicon project, which was very exciting indeed. Excuse me. Okay, so I want to start with this slide, and I think this really does demonstrate the importance of extracellular matrix. So this slide shows. This is a kidney on the left-hand side and a heart on the right-hand side. And you'll recognize this as a shape of kidney. It's a very characteristic shape. This is with cells and this is without cells. Likewise, you'll also recognize the shape of a heart with cells, without cells. The take-home message is you can take the cells out and you are still left with the shape of the organ. It's not functional, of course, because it doesn't have living cells in it. But it sends the message that, your shape and form is governed by your matrix. You are mostly matrix. In fact, you are about 70% matrix. If I just go back to that slide, if you take all of the cells out of your body, you're still left with a body that has the same shape. Take all the matrix out, and you're just a slurry, a puddle of cells on the floor, and nothing really very much else. So the matrix is what's giving you shape and form. Work started in 2000 and then 2010 told us that the main protein in that matrix is collagen, and that work told us that the turnover of collagen was extremely slow. The work done by Michael Kjær, I'm now circling his name here, Michael Kjær, who's based in Copenhagen in Denmark, did this beautiful work which was led by Katja in 2013, the C14 bond pulse data. And this basically showed us that the turnover of collagen in most of your tissues is 0. It never turns over. Just briefly explain what they did. So we know that between 1945 and 1963, there was above-ground nuclear warhead testing. When those nuclear bombs went off, they liberated C14 carbon dioxide into the atmosphere. That carbon dioxide was taken up by the plants, so they fixed the carbon dioxide, the C14. Cows and other animals ate the plants. We ate the plants, we ate the animals, we ate the cows, if you're a meat eater. And therefore, anyone living in this time were consuming C14, and that would get incorporated into their tissues. And if you now measure the amount of C14 in your tissues now, if you were born in that time or living within that time, C14 is the same, taking into account the natural half-life of C14, which is about 5,000 years. So I was born in 1957, around here. And if you measured how much C14 is in my tendons, my cartilage, my intervertebral disc, my cornea, it's the same. It's not changed. It's identical to within about 2%. It's identical. And that tells us that there is basically no turnover of collagen in your tissues. That reminds me of buildings like this. So this is Westminster Abbey in London. Maybe some of you have seen it. It's a beautiful building, truly beautiful building, made of stone. It was built in 1080. It was only built once. We built it in 1080, never been built. It's never been replicated. It is the same building. So like your collagen scaffolds, it was only built once. Of course, it needs to be maintained. You often see it covered in scaffolding like this. This isn't a repair. It's not been damaged. It's just routine maintenance. So what maintains your collagen in your tissues? If you made it by the time you are 17 years old, by the time you stop growing, you're going to live until you're about 100. How do you keep this? How do you maintain it? Why doesn't it break? Why doesn't it just decay or fail by fatigue failure? That's the question. How do you maintain your collagen scaffolds? Of course, work done in the same lab. I'm now highlighting Michael Kjær here. Michael did the same work, showing that in the same tissues, you see collagen synthesized, particularly after exercise. So there's a conundrum. These people have shown that you make your collagen when you're growing up, you keep it, you never replace it. And yet, cells have the ability to make collagen. And this is what really got us started. We started this work about, I'd say, 5 years ago now, and with our new funding. And we just published our first paper that came out in Nature Cell Biology just this year. So if you want the details of what I'm going to tell you in the next 10 minutes, take a look at this paper. At the end of my talk, I'll also talk about some labeling strategies that we're doing for matrix molecules. And although we've used procollagen, you can use these same strategies to labeling on whatever protein you want to look at. So if I don't cover it in detail, find them on the bioarchive. Okay, so insight into how you maintain your collagen tissues came from studies on the circadian clock, and I have to thank King Jun Meng in the bottom right there. He's a fellow at the University of Manchester and a great colleague to work with, and a very valued member of our staff. The circadian clock, so all animals and life on the surface of the planet is governed by cycles of light and dark. So tonight, when the sun goes down, you will feel sleepy and you'll go to sleep, and you'll wake up in the morning when the sun gets up. And your body clock is regulated by sunlight. So when you see sunlight in the morning, you pick this up within so this is by nerves which are not forming images, signals to a part of your brain called the tuberchiasmatic nucleus, excuse me, and that then sends signals throughout your body to synchronize your circadian clocks in your peripheral tissue. So it's not just limited to your brain. this brain clock communicates with all these tissues to generate a natural 24-hour rhythm. We understand the biochemistry of that to some degree. There's still much work being done, but the basic system of that is that when cells are synchronized, either by light in the brain or by other methods, by other chemicals and by other systems within your peripheral tissues, two transcription factors, BML1 and clock, are generated. They dimerize, they switch on a whole bunch of tissue-specific outputs, including two proteins, PER and CRY. These two proteins come together and they inhibit the function of BML1 and clock. So basically, you have a 24-hour system that's triggered by light and maintained by turnover of PER and CRY by degradation. If you put a reporter on this protein PER, you can literally see your tissues flash. So this is an Achilles tendon from mouse. You can do this in whatever tissue you want to look at, and you can see a nice rhythm that you can pick up, a nice 24-hour rhythm. I have to thank Chloe, who's now left my lab. She's now moved to Michael Kure's lab in Copenhagen. She was the one who really started this in my lab. So basically, you have a rhythm, and we asked the question, does that rhythm have anything to do with the collagen maintenance mechanism? And we turned to a tissue called tendon. Tendon is a very simple tissue. You can examine the collagen network simply by electron microscopy. We chose tendon, but we could have chosen other tissues as well. We could have chosen cartilage, we could have chosen blood vessels, we could have chosen skin, but tendon was the one that we knew most about. Simple experiment. We embedded tendon for electron microscopy, and we measured the collagen fibrils that you see within them. And the collagen assembles in these large structures that are centimeters in length, and are assembled in the extracellular matrix. This is one collagen fibril surrounded by its neighbors. They have a diameter, and this has been measured for decades. People have been measuring fibril diameters in all different conditions, from fibrosis through to cancer through to aging. And there's been a huge amount of controversy about what these diameters are, and people have basically said that they vary because of preparation conditions. We looked in the morning. This is 3 hours into daylight, and this is 9 a.m. and this is 9 p.m. and the diameters differ; they change. So this was the first indication that the extracellular matrix is rhythmic. It changes. It's not this static material that is laid down by cells and never changes. It is highly dynamic. Here we were just measuring the diameters of these individual ones, the smaller ones, which we call D1s, the larger ones D3s, and the intermediate ones D2s. They're repeatedly rhythmic. And this gave us the first indication that your extracellular matrix is regulated by the clock. Here we're using a technique called serial block phase scanning electron microscopy, where we are basically stepping through the tissue, almost like we're slicing through the tissue. And you can then look at how these individual fibrils change in shape. The schematic in the top, if you want to watch that, we show that these sort of larger D3 fibrils were very irregular, and actually almost the smaller D1s peeled off the surfaces, and the D1s are highly mobile. And this gave us an indication that the permanent matrix are these larger D3 fibrils, the larger fibrils, they're the permanent ones that are laid down when you are growing up. And the smaller ones, these are the circadian fibrils. These are the smaller fibrils which are surrounding the larger ones, almost like a protective matrix. So try and skip on now so that I don't waste too much time. We did transcriptomics through 2 days. We measured genes, about 745 genes that fluctuated with their levels during 2 days. Interestingly, the collagen genes are not rhythmic. So we knew that basically the rhythmicity of the collagen matrix is not driven by rhythmicity of gene expression. We looked back at our data. We saw a whole bunch of genes which were beautifully rhythmic. And when we looked at what these did, they actually are part of the secretory pathway. These genes regulate the amount of protein and the types of proteins being synthesized in the endoplasmic reticulum, traffic through to Golgi, traffic through the post-Golgi vesicles and exiting to the matrix. And the proteins which were particularly rhythmic are this one here, which is the translocon. It's the main protein that regulates protein translation. Another protein, Tango1, is pivotal in taking large molecules like procollagens into vesicles and sending them to the Golgi. PDEs, as many of you may know, are a large family of proteins involved in regulation of Golgi. This regulates the traffic of procollagen through Golgi, and then other molecules like 33B, which is the vacuolar protein sorting protein, which is involved in taking these compartments and taking them to the matrix. So the rhythmicity doesn't come from gene transcription of collagens, but from regulation of this secretory pathway. And that really told us that the mechanism that the cell is using is something called control theory. So control theory is a mathematical process or theory whereby you can regulate the components in an assembly line. So I've just used the Porsche assembly line from Stuttgart here. And so this is a car. It has one body, one hood, one windshield, 4 wheels, 2 gearboxes because it's a Porsche. And basically, when you assemble a car, you have to have the right components, the right number of components put on at the right time. And that's effectively what this is doing. It's making the proteins, it's modifying them, it's bringing all the enzymes needed to modify that to the right time, to the right place. And then when it's ready, it then transports it forward. It's modified here. These enzymes are switched on just when they need to be switched on. When it's been totally modified, it's then trafficked with time to the matrix. So this entire process is regulated by positive and negative feedback mechanisms, just as these plants are done here when you start to assemble vehicles. We knew that we could take these mathematical approach used by control theory, and this is now Ben Calverley within my lab, built this mathematical model to predict, using the levels of these intracellular proteins, can we predict where collagen is in the pathway and will it be secreted rhythmically? And the blue line is collagen. This is what's going to form those large fibrils. And the red line is procollagen. It's a precursor. And the prediction was that the precursor procollagen molecule would be rhythmic just ahead of the mature collagen. We went ahead and did proteomics. Very expensive experiment. Took us about 1.5 years to do. This cost about 30,000 euros to do this experiment. So it wasn't cheap, but it was a beautiful experiment. And I have to thank Joe and Venk and John in my lab for doing this. Turns out that in tendon, about 10% of your proteins are rhythmic. The stats were beautiful. They naturally separated into morning and night proteins. Most of the proteins made by these cells in tendon are produced in the morning or are produced at night. And interesting and really fascinating, when you measured the levels of collagen and procollagen, you could see that procollagen was here in black and collagen is present in red. And the predictions that Ben had made in this model were exactly what we saw by proteomics. So basically, by repeating this using other methods, we showed that actually procollagen is synthesized during the night. So this is the precursor, and the mature collagen is then pumped out of the cell in the within the morning and then through the day, beautifully showing that the secretory pathway is beautifully rhythmic. The prediction was that if we looked at a clockless mouse, so this delta 19 mouse has no functional circadian rhythm, we looked at their tendons and compared to normal tendon, which had the beautifully round fibrils, highly irregular fibrils. And this is a tendon-specific knockout of the clock. And again, highly irregular fibrils and differences in mechanical properties as well. So again, confirming that having a normal rhythmic circadian clock is essential for tissue health. And experimenting in cell culture, you can also take cells in culture, you can synchronize their cells, you can synchronize their clocks, look at the matrix being deposited and see stark differences in the levels of fibrils being deposited by these cells. So again, we can replicate in culture what we see within the mouse. And a last slide for this section is that if if you look in older mice, the old mouse loses its rhythm. So basically, this loss of rhythm, this loss of timing of when you deposit your matrix decays with time. And as you get older, the prediction in people is that when you get older, you lose your clock and you lose this nice rhythm and you lose tissue health. Let's not forget that your mobile devices like your iPhones give out blue light. They are a strong synchronizer of the clock. So when you read your emails or do your social networking at midnight, you are synchronizing your body to 6 o'clock in the morning. So be careful of this. This is a very powerful way of actually disrupting your clock. I've got about 4 slides left and then I'm done. I want to talk about briefly a system of counting collagen molecules. So we've used this molecule called nanoluciferase, taken from the deep sea shrimp. This animal uses it as a defense mechanism. It basically shoots luciferase out with a substrate, a flash of light, and its predator then chases the light, and this escapes. You can clone the enzyme, nanoluciferase. You can add a suitable substrate, which we've been using frimazine. You get a pulse of light, and so you can then quantitate how much light is actually coming from a protein. We know that on ProCollagen we've added one molecule of NLUC. We've now quantified this so that we can count the number of collagen molecules present at any time. It's very bright. It's about 1 million times brighter than GFP. In fact, Ben, my student who did this, was so happy when he did this. He made a 96-well plate. There are cells in all of these wells, and he then added the frimazine to just these cells and spelled out his name, which I thought was pretty cool. And so this is taken with an iPhone. It just tells you how bright this reaction is. Big thanks to Anthony, who's in our genome editing group as well, who actually helped us do this. With this, you can then visualize where your protein of interest is. I've used ProCollagen. You can use whatever protein you want to do, whatever's of interest in your lab. You can tag it, you can quantify it, you can get down to very high levels, you can watch this real time. So you can get over the problems of having to use promoters like CMV to drive GFP. You don't need to do that anymore. You simply crisp it in and look into whatever protein you want, and you can real-time monitor where it is. We've done this, of course, and we've now reconfirmed the circadian synthesis of ProCollagen, which is lovely. So the intracellular levels are beautifully rhythmic within our cells. Extracellular matrix is less so because basically it's being deposited. So you are depositing matrix and you're then adding a circadian levels on top of that. So in time that then levels out, which is totally predicted. But it was nice to see that we can actually measure collagen levels and they are rhythmic. Adam Pickard in the lab took this one step further. He took these cells, put them into a 96-well plate format. We purchased an FDA-approved library of compounds. You can do this, and use this to then quantitate how much collagen is being secreted or not. And so, without going into too much detail, you're looking for signals which are either actually like above this line or below this line. We then validated some of these compounds. We've got our top 10. These are our top 10 molecules from this FDA-approved library that are inhibitors of synthesis of collagen. Nintedanib is the industry leader right now. This is going through clinical trials as a treatment for idiopathic pulmonary fibrosis. And we would say that in addition to nintedanib, there are 9 other candidates that we are setting up now to do clinical trials on. Conversely, we've identified compounds which actually increase collagen synthesis. We can possibly think of these as being useful in problems, say wound healing. So these are our top 10, and again, we're setting up trials to investigate this. I'm going to stop there. I don't have time to go. I don't have time to talk about this. So I'm going to stop there, and I can take questions. So thank you.
Okay. Thank you, Carl. It's been really great, very clear, I think, for everybody. So I really enjoyed it. So let's say if we have questions already, you can read them in chat.
How do I get out of this?
There is a chat icon, so if you put the, but I can read them, no problem.
How do I stop this? I'm trying to think how I stop this. How do I? Can anybody help me? How do I get out of this display?
Just remove the sharing the screen. The Marco, can you help?
Okay, yes, okay. How about
if you just go back on the Teams. Yeah, there you go.
Yeah, there we go. Thank you, Marco.
Okay, so let's go to the questions, and we have one from Marco. He says, beautiful talk. Your data clearly show that having a regular circadian cycle is needed to keep tendons healthy. So do you notice any association between insomnia, sleep deprivation, or other circadian cycle influencing situations?
That's a really good question. We'd love to find out, and we're beginning to do some work with people in Manchester. Of course, we got this paper published in January, and then in March we had lockdown because of COVID. So we haven't been able to do any work in lab since March until about last week. So we've been dying to get back into lab to do some of this work. So we'll pick up on that, Mark, and that's a good question, and we'll try and do that. Yes, we're also trying to do some wound healing work as well. So we have some early results showing that if you knock the clock out in fibroblasts, there's a severe wound healing defect in mice. These mice don't actually heal their dermal wounds. So we are pretty confident that the clock is linked to defect in one cell migration, but also collagen deposition, leading to a wound defect. Yes. So yeah.
Okay, thank you. We have a couple of questions from Fabiana. As far as you know, is there any specific reason why procollagen is secreted during the night as opposed to during the day?
Yes, so I think this comes back to a question that I asked myself many years ago. So you're aware of MMPs, so these are proteinases that degrade collagens, and so there are proteinases that degrade collagen, and there are proteinases that actually are needed to actually deposit collagen. So these are the NSC proteinase, the BMPs, the BMP1, and the ADAMTSs. And it occurred to me that if you are building a tissue where the MMPs will degrade the protein and the ADAMTSs will deposit it, how does the cell know when to degrade it or when to leave it alone? So if you are putting in a protein and you want it to assemble into a matrix, you don't want MMPs there, do you? That would actually be working against you. And it turns out that the MMPs and the ADAMTSs and BMP1 are synthesized at different times of the day. And so basically, you are then secreting your collagen when MMP levels are low and assembly proteinases are high. So basically, I think what it's doing is to separate times of day when you build your matrix and when you turn it over. And you are effectively assembling, getting ready to make it at night when you are sleeping. So you are repairing at night. And in the day, when you want to start moving, your tissues have been properly repaired. They are good to go. So that's the best answer that I have at this time. You separate when you assemble, when you turn over, and you separate when you are damaging your tissues, as you are now. You are running around, you're exercising, you are moving, you're damaging your tissues, and tonight you're going to repair them.
Okay, thank you. Another question from Fabiana. Do you think in the future there could be research on restoring the circadian clock in older animals and humans?
Yes, I think I'm breaking up a little bit. Definitely. So there are companies like GSK who are developing chronotherapies. And in fact, some companies have already developed drugs that are active at different times of the day. So not only collagen, but many other proteins are circadianly regulated. Some of them are drug targets. And basically, if you are synthesizing a kinase, let's just pick a kinase, you are synthesizing a kinase at night, and you want to inhibit that kinase, it doesn't make any sense to be taking your kinase inhibitor in the day. You should be taking it at night. So companies like GSK are developing drugs that you consume in the day and they become active at night when the target protein is ready. So big pharma are definitely thinking along these lines, yes.
Okay, thank you. A question from Michela. Do you think that this circadian regulation can also affect other cells linked to collagen, for instance, osteoblasts?
Definitely. So we've only, basically there was, I think it was, who was it? I can't think who it was now, but there was a paper many years ago showing that bone is a peripheral clot tissue. No mechanisms have been linked to that yet. I think we're the first one to actually link a mechanism that what the clot does to biochemistry of the cell. But we know that osteoblasts are strongly regulated by the clock, and I think we're waiting for new people. You maybe come and do the work. You know, you guys have a look at the circadian regulation of osteoblasts, and you will see proteins that are regulated differently day and night. I know that King Jun Meng, who I mentioned earlier, King Jun is really interested in cartilage, and he's shown that if you look at chondrocytes in mice, they are strongly regulated by the clock, polyglycans in particular. So I think all cell types are regulated by the clock. I know that John O'Neill, who's at LMB in Cambridge, he's looked at red blood cells. And red blood cells obviously don't have a nucleus, but they have some kind of rhythm that is persistent in the red blood cell. So even the cell in which you've taken a nucleus out, there's a remnant of a clock. So basically, all cells in your body are clock regulated. Yeah.
I have a question for you. Do all collagen types have a circadian clock? For instance, fibrillar or non-fibrillar, or is it just a matter of collagen 1?
No, we find in tendon and other tissues too, collagen 1, collagen 5, collagen 6 are the main collagens which seem to be rhythmic. Collagen 12 and 14 are present in low levels, and of course, if you're using proteomics, you get a much better signal, a much more reproducible, a statistically more important signal if your protein is abundant. But if you look very carefully, you can see some rhythmicity in 12 and 14. But obviously, because type 1 is so abundant, it's so easy to pick up that nice rhythm. But I can confidently say that type 1, type 5, type 6 are the ones which we've looked at, and they are beautifully rhythmic, yes.
And another question that I have is the loss of rhythm that is seen in aging is only central due to neural failure, or there is also something that happens in the peripheral tissues?
Very interesting what happens with age. It's not something that we're leading in right now. I know a lot of people have picked up on this. Your brain clock doesn't seem to age. So your suprachiasmatic nucleus, which is your brain clock, doesn't age. That is rhythmic all the way through life. But your peripheral tissues like tendon and cartilage, they do age. And also, which I didn't have time to actually pick up on, but the phase lag between the brain clock and the tissue clocks ages. So basically, for the younger people in the audience, when you saw sunlight this morning, your suprachiasmatic nucleus became synchronized, and immediately they sent signals to your adrenal glands sitting above your kidneys. They sent out cortisol throughout your body, and the cortisol within minutes synchronized your peripheral tissues. Within older people, there's a time delay. So I'm 63, so I would predict that when my brain clock was synchronized this morning, there was approximately a 6-hour lag before my peripheral tissues wake up. And that's why I think a lot of older people have difficulty getting going in the morning. It takes them time to have their breakfast, to get up, and by about lunchtime, I can see Anna smiling here, by about lunchtime, they're kind of getting into their day. So maybe that's linked to this lag between brain clock and your tissue clocks.
Okay.
No, you are. I didn't mean to mention you're fine.
Okay, I don't see any further questions. I think that this talk has been really very, very interesting. And yeah, it's nice to see you again, Carl, and nice also to see that you are tightly collaborating with Michael Kier. So that is really very nice, and I enjoyed to work with you in the Rubicon project. Okay, thank you very much, and let's keep in touch.
You have a nice day. I hope it all goes well. Take care.
Thank you.
Okay. Bye-bye, bye-bye, everybody.
Bye-bye. So thank you. We can now move to the next presentation that is by Fabiana Tennant. She is from the University of Manchester, but she spent 1 year, almost 1 year, with us as a student in placement. And Fabiana will talk about the role of extracellular vesicles in osteosarcoma progression. So Fabiana?
Sorry, I'm having some trouble to share my screen.
Can you explain the problem?
I'm clicking on share desktop and it's not coming up with any options.
It was
okay,
working.
Fabiana, maybe we can move to the next presentation so you have time to solve it and you will talk immediately after that.
Okay.
Okay. So let's move to Sara Ponziani from the University of L'Aquila. Sara, are you there?
Yes, I'm here.
Okay. Sara will talk about the ADC in anti-tumor therapy, where ADC stands for what?
Okay.
I think antibody-drug conjugates, right?
Yes. And just try to share, but as Fabiana, I can't maybe. I try to open again my PowerPoint.
Marco, is it possible that Carl didn't close it? No, but he did.
Yeah, he did. I think the problem is with the computers. It was working yesterday when we tested, so.
So, Sarah, are you having problems as well?
Because I say no disponible file for PowerPoint.
How about leave the connection and reconnect? Would you like to try that?
Yeah, maybe Fabiana can also try the same.
So disconnect and reconnect. And we move to Lucia Di Nardo, let's see, from the Catholic University in Rome.
Yes.
Lucia, you're there?
Yes.
Can you check if you are able to to share the screen?
I try. Okay, you can see?
No. I see you, but not the screen.
Okay.
Here we are. Okay, great. So let's go with Lucia. She will talk about next generation sequencing analysis to identify molecular alterations in different basal cell carcinoma subtypes. And then we will go on with the other two presentations. So go ahead, Lucia.
Okay. My name is Lucia Di Nardo, and I am an early postdoc at Catholic University, and our study has been focused on the molecular landscape of basal cell carcinoma. Basal cell carcinoma accounts for 80% of non-melanoma skin cancer, which is one of the most common diagnosed neoplasm among the Caucasian population, much more frequent than melanoma, with an increasing incidence rate of fourfold in the last 4 decades registered in Europe. Sporadic BCC are a very heterogeneous group of tumors showing a great variability in morphology and aggressiveness. And the superficial and nodular BCC, although grouped as non-aggressive, slow-growing lesion with low risk of recurrence, account for 80% of BCC cases, thus representing a growing healthcare issue. The aberrant activation of the edge signaling pathway involved in the regulation of cell type differentiation and adult tissue homeostasis is known to play a pivotal role in the pathogenesis of BCC. And the expression of mutated patch1 or SMooth protein triggers constitutive activation of edge signaling. Alteration in the cell cycle regulator TP53 gene are the second most prevalent tumorigenic event in primary BCC. However, recent exon sequencing studies have shown that sporadic BCC have one of the highest rates of somatic mutation of all cancers, involving additional genes and pathways besides edge aberrant activation, with growing attention on the regulatory sequencing of the human genome, especially TEP promoter and DPH3 promoter. So the main objective of this study was to identify molecular alteration other than patch-related pathway that might contribute to carcinogenesis, closely tied with potential clinical impact. And furthermore, we aim to describe the mutational profile in a series of primary superficial and nodular tumors in order to provide fundamental insights into the molecular subclassification of BCC. So 57 BCC biopsies and matched blood samples were collected and DNA from all samples subjected to library preparation in order to perform targeted sequencing on Ion PGM system platform. BCC-specific target panel was designed with Ion AmpliSeq technology, including 12 target genes, while TEP promoter region was analyzed by direct Sanger sequencing. Tumor germline matched data were then processed for somatic variant calling and annotation in order to exclude variants identified in both samples and to distinguish driver from passengers mutations. So our in-depth analysis led to the identification of somatic variant in 98% of BCC, consistently with the high tumor mutational burden previously described. 72% of tumors harbor mutation in patch1 gene, with 16 BCC carrying more than one patch1 alterations. Patch1 mainly exhibited a spectrum of point mutations with a predominance of truncating ones, and mutations were observed throughout the entire coding sequence with no specific hotspot region. TP53 was found to be mutated in 45% of BCC, and mutations were predominantly missense, involving the DNA binding domain, followed by truncating mutations. No hotspot mutations were detected at protein position 177 in 2 tumors and 196 in 3 lesions. CSMD1 protein is a no inhibitor of the complement system. Proposed to act as tumor suppressor gene was inactivated function due to copy number loss, gene expression loss, or somatic mutations, was found significantly associated with poor survival and high disease stage in many cancers, including non-melanoma skin cancer. In our sample series, mutations in CSMD1 were found in 63% of BCC, with missense variant being the most prevalent. In addition, more than one CSMD1 alterations was found in 22 lesions. All the identified CSMD1 mutations were not listed in the oncology knowledge, ClinVar, Cosmic, and Intervar databases. However, they applied prediction tool revealing that 42% of these mutations were damaging for protein function. NOTCH1 can function as both an oncogene and tumor suppressor gene depending on cell type and context. It has been demonstrated that NOTCH signaling pathway is suppressed in BCC tumor, and NOTCH1 loss of function mutations was found to specifically promote tumor persistence in BCC, in sporadic BCC. We found NOTCH1 mutations in 44% of lesions, mainly consisting of truncating mutations, thus supporting its tumor suppressor role in BCC tumorigenesis. As for the regulatory region of genome, we found TEP promoter mutations in 58% of tumors. BCC tumors with TEP promoter mutation were previously shown to have an increased transcription of TER subunit and shorter telomere compared with tumors without these mutations. It has been suggested that critically shorter telomeres triggers genome instability, and telomerase is then upregulated to sustain cell proliferation and tumorigenesis. We found DPH3 mutations in 39% of BCC. However, the effect of DPH3 promoter mutations on transcription of adjacent or distant genes remains currently unclear. We then evaluated the distribution of alteration in the 7 different loci that display 2 possible states, wild type or mutated, and we found significant concurrent mutations of TP53 gene with CSMD1, PETCH1, and DPH3 promoter. We further investigating the association of a specific mutational profile with the superficial or nodular subtypes. With the PCA, principal component analysis, a multivariate statistical approach, reveal PETCH1 mutational profile as the characterizing variable of the superficial subtypes. So, in conclusion, we confirmed the high prevalence of mutations in edge of pathway together with the high rate of mutations in CSMD1 and OCH1. In addition, we found certain DPH3 promoter regions frequently mutated. Interestingly, CSMD1 mutations significantly concurred with TP53 changes, which may be linked to treatment-related heterogeneity. Finally, we found PETCH1 mutations to correlate with the development of superficial BCC. So altogether, our findings offer detailed knowledge about the molecular alternation underlying tumorigenic mechanism of BCC, which is highly needed to direct novel rational-based treatment strategies. Thank you for the attention.
Okay, thank you. Very interesting. Is there any question? I don't see anyone in the chat. I can start, maybe. So, for instance, you have a group of genes that are mutated that you showed in your presentation. Do you know which type of functional consequences have this mutation? For instance, Notch1, is it activated or is it inactivated, or the others, of course? So do you have any kind of functional...
Okay, in our cases, Notch1 is inactivated. The majority of the mutation is truncated mutation. So we applied for, in particular, CSMD1, for which all the identified mutations were not listed in the ClinVar interval databases that we commonly use for linked the genomic variant with the protein damage and treatment relationship. And we found that about 0.5% of the mutations is damaging for protein function. And to do this, we used a bioinformatics help that is characterized by a database which includes several prediction tools like SIFT, Proven, Polyfen, and but functional study we don't have previously functional study in vitro. Okay, we use this prediction tool.
Okay. So I don't see any further question. Just another curiosity, do you find only Notch1 mutated or also the other notches can be mutated?
No, only Notch1, and for CSMD1 or 2, only CSMD1. Okay. So this is interestingly because previous report indicates also Notch2 or CSMD2, but we have a really shorter simple series 57 that like the others. Okay.
Maybe you need a larger population to have a better statistics. Yes. Okay. If there are no further questions, I'd like to thank Lucia very much. And let's see if Fabiana solved the problem. Fabiana, you're there?
Hi. Yes, I think I managed to solve it.
Okay, good. Problems?
Sorry, my computer.
No way.
It's.
Can you send the presentation to Marco, and maybe Marco can show, and yeah, you tell him when. Yeah, let's do this way, and let's see Sarah. Meanwhile, if you are.
Yes.
Yes. Okay, thank you. So go ahead.
Okay. So, good morning everyone. I'm Sara Panziani. I'm a PhD student in molecular biology, and my project is about the use of ADC for the treatment of tumors. It's an ADC. It's a monoclonal antibody that is usually joined to a payload through a linker. The nature of linker is the creation of an internalizing conjugate or not, and the strategy of conjugation can be chemical, random, or site-specific, like the one I want to show you now. In general, the mechanism of action can be internalizing, that is, the antibody must first penetrate the cancer cells to be degraded and then release the drug, or not internalizing, which has a more immediate effect because it already acts in tumor environment. We have focused our attention precisely on this last mechanism. The system on which the conjugates are based is the drug delivery, that brings the payload in the body in a specific way. Unlike the classical chemotherapy, the transport of the drug through a vehicle, like an ADC does, reduces the degradation and increases the solubility of the drug, as well as increasing its bioavailability at the target site, reducing the specific in the body. Our cellular target is the Decay, a protein that is secreted in a large amount in the extracellular matrix of many cancer cells. Here you can see the fluorescence image of the localization on the membrane of this protein in breast cancer cells and in melanoma A375 cancer cells. On the other hand, you can notice that there is not so much expression of Decay in normal fibroblast bronchial cells. So, to carry out this experiment, we first choose an anti-Decay antibody. We humanized it to make it less immunogenic, and finally it was engineered to make the conjugation site-specific. To do this, we changed 3 cysteines in the injured region in 3 serines, and so we left only 2 cysteines free on the light chain to attach the payload, that in our case is a thiolated one, through a disulfide bound. This modification allows us to bind only 2 molecules of drug for each antibody. Downstream of the conjugation, we check the quality of the conjugate. At first, we did a reverse phase chromatography with HPLC to calculate stoichiometrically the number of moles drug present in the conjugate. After, we carry out an hydrophobic chromatography with a specific column to recognize the DAR, that stands for drug-antibody ratio, which explore the increase in hydrophobicity of the conjugate compared to the naked antibody. Both chromatographies confirm that the results is equal to 2. To be more sure, we tested it also in mass spectrometry, and we reached the same result. The mechanism of action of our ADC is quickly summarized in this picture. The conjugate, through the circulatory system, reaches the tumor environment that has Decay. This is a reducing environment that contain some glutathione and cysteines that broke the disulfide bond that lead the drug to the antibody. The drug enter into the cells and start to kill tumor cells. The death of the cells release other cysteines and glutathione that increase the release of drug from the conjugate in a catalytic way. We tested it in ELISA to confirm the affinity of our conjugate for 90K that is compared to the naked one. And in vivo, we take some mice CD1 in which cells A375 human melanoma cells have been injected via xenograft. And the treatment was conducted in a group of 6 mice with 2 schedules of administration of 10 milligrams per kilos of treatment for each mouse. And as you can see in the scheme, after about 28 to 35 days, we have the completely eradication of the mass tumor. So, in conclusion, we can say that it works, and maybe we can investigate in other kind of cancer disease, like also in the hardest one, like neuroblastoma, for example. I want to thank my project collaborator, in particular Professor Rodolfo Ippoliti, and you for your attention. Thanks.
Okay, thank you very much, Sarah. I see Simona Delle Monache who raised her hand. You want to ask a question, Simona? Just unmute yourself in case.
Sorry, no question.
Oh, okay. Okay, is there any other question? Yes, I see something here. Just 1 minute. Okay, Michaela, which kind of side effects can have this treatment?
Side effect just only to other tumor cells, not so much in FT cells, so it's a very specific treatment. In fact, we have not noticed any toxicity in for the mice, for example, because no one of them was died during the treatment.
Do you think that this method can be applied to different drugs, or is
Yes.
something?
We just did it. In fact, I show you just one of the kind of the conjugate that we done, but for sure we attached all the possible drug to all possible antibody this time.
Okay, we have Antonio. Probably I miss it. Are you using vehicle for delivery the antibody? And what about the distribution in vivo?
The antibody is the vehicle, so it recognizes the his target that is this protein in the variable region of the antibody. It reaches his target, that is this region on the 90K protein. And for distribution, we noticed that it's very stable compound. In order to, there is no toxicity in mice, and so it arrived. And we did also some release test in HPLC system, just to check the stability of the compound. So it's a good compound.
Okay, thank you. I don't see any further questions, so thanks a lot, Sarah.
Thank you.
Let's move to Fabiana again. So Fabiana, did you solve the problem?
I think so. Can you see my screen?
Yes. There is an echo. Try to switch off the microphone for 1 second. We see the screen, yes. Okay. Try again. So the screen disappeared. Marco, can you help? Did you receive the PowerPoint presentation?
No, it was too heavy, she said, and yeah, but she solved it. She just disappeared.
Sorry?
She just disappeared. No, it was
Yes.
working now.
Fabiana, can you hear us?
My laptop, so I'm going to send the PowerPoint. I'm sending the PowerPoint to Marco, and then he can show the PowerPoint to our commentators.
There is also a problem with the audio, Fabiana. If you want to send to Marco, you can save it as a PDF.
Okay.
Yeah. And switch off your microphone. Yeah. So unfortunately, we have to wait.
Sorry, Fabiana, if you want to speak, reactivate your microphone. I just muted you because we heard a lot of echo.
She could also share a Dropbox with you, but yeah. Is anything happening, Marco?
Yeah, we are speaking over the phone. Yep. Okay. She sent me the presentation. So.
Okay. So you can share the screen, and Fabiana just say next slide, and Marco will.
Okay, just give me a minute because I have to download it.
Is the audio okay?
Yes.
Okay. I'm so sorry.
No problem. Okay. The connection is never perfect.
Yeah.
I'm almost sitting on the roof of my house to have a good connection. So,
yeah.
And I hear funny stories where people is sitting on.
Okay, almost there. Just sharing the screen now. All right. So I'll just let me just mute myself, and then Fabiana, when you want me to go forward, just say next slide.
Okay. Okay, so first of all, my name is Fabiana Tennant. I'm a student from the University of Manchester, and I've done a placement year here at the University of L'Aquila in the Skeletal Diseases Lab. And today I'm going to talk to you about my project, which is called The Role of Extracellular Vesicles in Osteosarcoma Progression. So you can go to the next slide. Okay, so for those of you that don't know, osteosarcoma is a primary bone cancer, so I'm going to be speaking about the bone. And the bone is a very important organ with lots of different functions. So in order to maintain its integrity, it's constantly replenished by a turnover mechanism called the bone remodeling process. And bone remodeling is orchestrated by the balanced activity of the bone-forming osteoblasts, which are shown in this diagram in blue, and the bone-degrading osteoclasts, which are shown in red. So just briefly, osteoblasts express ligands such as rank ligand and macrophage colony stimulating factor, and osteoclast progenitors express receptors to bind to these ligands, and this results in the activation of osteoclast progenitors to mature osteoclasts, as shown in the red cell at the bottom, and they can then degrade the underlying bone matrix, and whilst this happens, growth factors are released which stimulate osteoblast maturation, and osteoblasts can then deposit new bone in the empty spaces, therefore closing the remodeling cycle. Next. So moving on, extracellular vesicles, or EVs, are complex membrane-derived nanostructures which for a really long time were considered to be just products of cell debris and waste. But however, in recent years, they've been discovered as a regulated and programmed means of cell-to-cell communication, whereby they can transport functionally active proteins, lipids, mRNAs, and microRNAs between cells. Furthermore, EV-mediated communication has been shown to actively participate in the bone remodeling process and cancer progression. Next. So, therefore, we decided to investigate how osteosarcoma-derived EVs educate the bone microenvironment using the Hoss osteosarcoma cell line. Next. So the first thing that we did was perform a series of technical controls to validate the quality of our EV preparation. So we isolated the Hoss EVs using a method called differential ultracentrifugation, and the first thing we did was perform a Western blot analysis for EV markers, which are proteins that are typically highly expressed in EVs, such as annexin-2 and CD63. And we found high expression of both of these proteins in the EV extracts. And this was complemented by a transmission electron microscopy analysis of Hoss EVs, which confirmed the correct vesicular structure and also the membranes were still intact after the ultracentrifugation. Then finally, we performed a confocal microscopy analysis to demonstrate that fluorescently labeled EVs integrated into both osteoblasts and osteoclasts in vitro, as you can see in the two bottom figures. So this is confirmation of a direct interaction between the EVs and the bone resident cells. Next. So following this result, we then wanted to understand the effects of Hoss EVs on osteoblast viability and transcriptional profile. So the first thing that we did as a preliminary experiment was perform a time course analysis where we treated osteoblasts with Hoss EVs and evaluated metabolic activity, cell number, and alkaline phosphatase activity, which is a marker of osteoblast differentiation. And what we actually found was that upon treatment with Hoss EVs, all three of these parameters were markedly reduced, which indicates that Hoss EVs exert a very quite a malignant effect on these cells. Subsequently, we performed a transcriptional analysis, so at the RNA level, and the first thing we found was a significant reduction in the expression of osteoblast differentiating genes in osteoblasts treated with Hoss EVs. So this complements the previous result for the alkaline phosphatase activity and also demonstrates that Hoss EVs have an inhibitory effect on osteoblast differentiation. Interestingly, we didn't see any significant differences in the expression of osteoblast-osteoclast coupling factors, which are important in regulating osteoclastogenesis upon treatment with Hoss EVs, but we did see a very substantial increase in the expression of pro-inflammatory cytokines upon treatment with Hoss EVs, and these can be implicated in promoting osteoclastogenesis and also promoting a pro-tumoral environment. Next. So, following this last result, we decided to evaluate the effect of Hoss EVs on the osteoblast cytokine profile. And so the latter result was confirmed at the protein level by an ELISA assay and a cytokine array, which are plate-based and membrane-based assays respectively, used for evaluating protein cytokine expression. And we found that in the conditioned medium from osteoblasts treated with Hoss EVs, there was a significant increase in protein expression of an array of pro-inflammatory cytokines that can have pro-tumoral and pro-osteoclastogenic effects. Next. So then we decided to evaluate the effect of HOS-EVs on osteoclastogenesis, as the pathogenesis of osteosarcoma is actually characterized by osteoclast-mediated bone destruction. So interestingly, we didn't find any increase or any changes in osteoclastogenesis upon treatment with HOS-EVs, but we did notice that cell number was markedly increased by treatment with HOS-EVs, and that the appearance of the cells was quite unusual. So this indicates some malignant effects of the HOS-EVs. And after that, we then treated the calvaria of mice, which is the top of the skull, with HOS-EVs, and we found that, and also DMEM, which is a control, and we found that upon treatment with HOS-EVs, there was a significant reduction in bone volume, and we're now performing histomorphometric analysis to determine if this result could be to a change in osteoblast number or osteoclast number. Next. Then we decided to evaluate the effects of HOS-EVs on in vitro angiogenesis, as of course angiogenesis is a hallmark of cancer. So we treated human umbilical vein endothelial cells, or HUVECs, with HOS-EVs. And the first thing that we performed was in figure a crystal violet assay, which is used to estimate cell number. And we found that upon treatment with HOS-EVs, HUVEC cell number was quite significantly increased. And then figures B and C, we performed a branching assay, and we found that once again upon treatment with HOS-EVs, there was quite a significant increase in blood vessel formation. So these data suggest a pro-angiogenic effect of HOS-EVs on HUVEC cells. Next. Finally, the next stage of the experiment, we decided to investigate the effect of osteoblast-derived EVs on host cell phenotype. So the opposite way round, as there is a growing amount of literature showing that the tumor microenvironment feeds back to support cancer progression. So we decided to evaluate parameters that are particularly generally abnormal or accelerated in malignant cells. So we first looked at metabolic activity and proliferation. And we found actually that in host cells treated with osteoblast EVs, the metabolic activity of these cells was quite significantly reduced, which was quite an interesting finding. However, we didn't see any differences in host proliferation upon treatment with osteoblast EVs. Next. And finally, we decided to evaluate motility and invasion, as of course these are two very important parameters for cells to colonize, malignant cells to colonize and also migrate into different areas of the body. So we performed a scratch wound heal assay to evaluate motility, and we found quite a significant reduction in the motility of host cells upon treatment with osteoblast EVs. And then furthermore, an invasion assay whereby we used Matrigel, which is basically a model of the basement membrane. We also found that the invasion capacity of host cells was quite significantly reduced by treatment with HOS-EVs. So all in all, this could suggest a inhibitory effect of tumor progression by osteoblast EVs. Next. So in conclusion, we demonstrated that HOS-EVs are internalized by bone cells and potently reduce osteoblast viability and differentiation. HOS-EVs increase angiogenesis and the release of pro-inflammatory cytokines in osteoblasts, and osteoblast EVs appear to exert a novel reduction on host cell metabolic activity, motility, and invasion. So I'd like to thank my lab and also the TMS committee for the opportunity, and I'll take any questions. And also, very sorry for the technical difficulties.
No problem, Fabiana. These things happen. Actually, I have to say thank you for being with us for almost 1 year. And this is the end of the placement, so we will miss you, of course. So is there any question? I have one. Since this EV has a tropism for the target cells, did you test it, or you think to test drugs that can be uploaded in the EVs for and use the BEVs as a vehicle, or is this something that cannot be done?
Okay, so not me specifically, but actually my lab before I arrived, they loaded osteoblast EVs with anti-osteoclastogenic drugs and actually found that they delivered with quite high efficacy to the bone microenvironment in vivo. So yeah, it can definitely be done.
Another possibility could be also to genetically manipulate the EVs to improve the targeting, specific targeting to the cells that you want to kill, or
So I would think so. I mean, obviously the advantage of EVs is that they are biological, they derive from within the body. So say, for example, with the last section, the advantage of osteoblast EVs impacting host cells so much would be that they arise within the same environment, so they could be targeted to host cells with quite high efficacy. But certainly, I'm sure they could be genetically modified too as well to improve the targeting.
Yeah, I see Antonio also asked the question, in light of your results, do you think that treatment with empty osteoblast EVs could impact the osteosarcoma growth in vivo?
So I hope so. I mean, we haven't done the in vivo experiments yet, but the in vitro experiments are quite promising. So I think that will probably be the next stage of the lab to do the in vivo experiment.
Okay, come back here. I cannot see you anymore here. Okay, so no other question. Let's see if probably there is a hands-on. No? Okay.
Sorry.
So, sorry?
Sorry, I'm not a member of the team, so I cannot write in the chat. I have a curiosity for Fabian. Have you an idea of the time of incorporation of extracellular recycle on osteoblast?
Yes, so in the osteoclasts or the...
On the osteoclast?
Yeah, so the osteoclast, so we normally do a treatment period of 24 to 48 hours, depending on the specific experiment, and that's enough time. So they do incorporate quite quickly, but in order to see a phenotypic difference, that can sometimes take a bit more time. For example, with the scratch wound heal assay, actually, the first few experiments we did, we directly treated the cells with the osteoblast EVs, and we didn't see that much of a difference, and subsequently we decided to do a pre-treatment of 24 hours, and we saw a much more significant difference. So I would say 24 hours is definitely more than enough time.
Okay, thank you.
Thank you.
Okay. I think we don't have any further questions, so thank you very much, Fabiana. I think that this is the close of the session, and I'd like to thank all the participants for the high quality of the presentations. Thank you. And I hand over now to Marco, I think, for the award presentation.
Yes, so we will now take just a 10 minutes recess to, and I will invite you into another room to, let's say, discuss the winners of all the sessions. So please, nobody leave the room here. We will be back in 10 minutes to announce the winners for all the sessions. Thank you. Okay, so we are back. We have our winners for the Day of Science. And we just want to thank our sponsor CIAL for giving us the opportunity of having this kind of awards for this. And we just want to point out that the revision process was absolutely unbiased and done by external people, or it was absolutely 100% free of conflict of interests and things like that. So we will just proceed in chronological order. So we will start with the physics awards, which will be presented by Francesco Salamida.
Okay, so first of all, I thank all the two speakers that participate to this day, that are Valerio D'Andrea and Riccardo Biondi. So for physics, the best presentation of the two is the presentation from Valerio D'Andrea about Gerda and Legend experiment. I don't know if Valerio is here to, let's say, virtually take the prize. I don't know. Probably not.
Yes, I'm here.
Ah, okay, Valerio. So congratulations.
Okay, thanks.
So there is no bias, as Marco said, for this prize, because I say because I know you very well. But there is for sure no conflict of interest in the decision. So thanks a lot for your time, and thanks a lot for the nice presentation, and also thanks a lot to Riccardo for the nice presentation and for participating to our TMS Day of Science. Thanks a lot. So I think is the I give the word to Luisa, right? Okay. Yes. Thanks a lot.
Even for chemistry, we have the winners. That for the oral presentation, the winner is Vincenzo Marzicano. Whereas for the poster, the best poster was chosen was the one of Valeria Nori. So I don't know if Vincenzo and Valeria are listening. So congratulations to
thank you
to both of you, and in general all the poster and all the presentation were appreciated from the committee. So let's skip to biology.
Okay, so Professor Teddy, we cannot hear you. You can activate your microphone.
Yes. Yeah, we also have the winner. I want to make. Okay, so the best oral presentation is from Lucia Di Nardo. Congratulations, Lucia, you're there.
Thanks a lot. Yes, I'm here.
Thank you. And the best poster is Fabiana Tennant. So, Fabiana, are you there?
Thank you.
Okay, so congratulations to all. I think that has been really a great session for everybody. So it would be nice if all the winners can show up with their camera on. So we can take a picture maybe, and then maybe everybody can switch on the camera so we can show that we are a very strong group. So can also the other winners switch on the camera?
Mm-hmm. So we have also two more winners.
Oh, okay, cool.
And they can activate the camera as well. And the first one is Iona Norwood, who asked the most questions during the TMS seminars during the year. So Iona, congratulations, you can activate your camera as well. If you can. I see you're connected, but if you don't have a camera, it's fine. Okay, there she is. Hello, Iona. And the last, let's say, winner, which wins the TMS Friend title, is Maurizio Gironi, who is not winning any physical prize except a promise from me to buy him breakfast. So, Maurizio, can you activate the camera as well so we can take a picture?
Okay, so do we have everybody? Because I cannot see all of the people. Do we have everybody?
I'm missing the chemists in my...
They are connected, but...
I think we can only fit like 6 people in the screen.
Okay. Okay.
So the bigger this gets, so you can all take a screenshot. You are probably seeing different people than me, and then you can send to me. Okay? So smile.
Thank you. And congratulations to everybody. Okay, so Marco, it's your turn to close the meeting and tell us what is next and when everybody are invited to connect again.
Yes. So first of all, thanks to everyone who attended this day of science. Thank you to all the collaborators, especially the external ones from the other universities. I think it sends a very nice message when you see, departments that usually don't communicate with each other and universities that don't actually like each other that much to just come together in an event like this. So thank you to all who participated. And this is the last event for this year for the TMS. So we will see you next year in September, the next academic year. So we will be back in the first Thursday of September, which is the 3rd. So we won't leave you alone. The first Thursday available, we will be there. It will be a webinar in biology. And if you're interested, of course, we will still be here on the Teams. And for now, we will just keep this method of communicating with you. So we will still keep our seminars on the Teams. And if that changes or we go back to a hybrid form, we will let you know. And I also want to thank Fabiana and Antonio for helping with the organization of this day. And again, all of you and the executive committee and the TMS committee for really making this possible. So, thank you.
Thank you, Marco. And for those who are not based at the University of L'Aquila, we are open to everybody. So if you want to contribute, and yeah, that would be great, especially because probably we will continue with the virtual meeting for a while, and after that, when we will have face-to-face meeting, probably we can have a kind of hybrid connection, so even people who are not living in L'Aquila can connect. Okay, thanks a lot. Bye-bye.
Thank you. Bye-bye.
Bye.